One, two. Wapi bon. Kasi yango yedi. Okisi kote. Yango hapana. One. Yango wana. Ozoka te. 1, 2, 3, 4, 5, 6, 1, 2, 1, 2, 1, 2, 1, 2, 3, 4, 5. Zela no, zela zaka wana pardon. 1, 2, 3, 4, 5, 6, 6, 7. Yeah. Clear. Ladies and gentlemen, welcome to the DDD. No confusion on in. Ah, tata. Onyo kolanga veli kam. Tata. C'est bon. e yango wana donc eza off nde te donc tika o on e zela pardon zela two one two one two one two yeah tika ngo on one two ladies and gentlemen can you zoom sikoji na recording peut-être ndelo pe bata zoom yeah et 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 yebo one two yeah yeah et 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 the end omona ngo one 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 tala kuna omoni na che off na tindi one two three so che ataba écouteur dans oro dans oro yokanga omoni so na lobi one two 1, 2, and 2, oh, 2, A, eh. Uzoka ngothi 1, 2, 3, 4, 5. Is ready? 1, 2, wananga muno cheke.
I'm like a guest listening as well.
You like a guest listening?
Yes, yes. Now check again. I need
Is anything going on here? I can't hear anyone. I can hear anything.
for our low resolution image from the observation through to the auto encoder, we provide for the good super resolution images. Then through to the regression, we just estimate about for the black hole spin and the high, R high value onto there. So we combine about for the pre-trained to the autoencoder and to the CNN regressor, provide for the good fit model even for the low resolution image onto there. So this is our the preliminary result onto the. We try to estimate of the black hole spin onto the R high value onto there using about for the five different observational data onto there. So I think most is the highest resolution is coming from to this one. So April 6th. To combine together, and then to the EHT is still continuously observing from the 2018 to 2024. And now it's including for the 3 new telescopes participated onto the EHT collaboration. Then now we are starting about for the developing for the next generation EHT. Is talking about for this one. So the more telescope and the higher frequency is roughly 1.5 times higher resolution we obtained there. We also making for some plan to making about for the black hole explorer. So this is the space BLBI project. Connecting for the satellite and to the ground BLBI to obtain about for the first signature of the photon ring emission onto there. Okay, so this is the summary. So the EHT has seen the black hole shadow image in the MS7, which is the signature of the light bending in the rotating black hole. And then based on the shadow size, the black hole mass of the MS7 is very measured, which is consistent with the stellar kinematic value. In the polarization image, the high polarization region follow to the bright ring structure with a helical EBP pattern from the model comparison. So the matte accretion model is favor over than to the SRNA model. So finally we can show to this one the machine learning may provide more constraint on the black hole spin. We hope we can get in for some more result onto that. Yeah, that's all. Thank you very much.
Very much. Thanks very much. Okay, we have time for some questions. Sure. I'll go with you. Go ahead.
Hello, nice talk.
Yep.
I want to ask, have you tried to fit the broadband spectral energy distributions of M87? And if so, that the prescription for electron beam?
Yeah, so I think it's we taking about for the multi the wavelengths observation, and then to the in the IAU the Sarah is talking about for this multi wavelengths observation result. So not there. Yeah.
Hi, very nice talk. I saw you went with a classification model for the estimation of black hole spins. Have you experimented with the regression model?
I'm sorry.
Have you experimented with regression model for the estimation of black hole spins rather than a classification model that you showed in the two slides ago?
Yeah, I think it's normal.
Yeah.
This convolutional neural network show about for the very hard to determine about for the black hole spin. But this is a little bit older work. Now recently we are using for the more advanced regression model to obtain about for the black hole spin how much it's determined to there. But still, this is unfortunately this is still preliminary result. I cannot say result so much here. Okay.
Other questions? If you had, oh, yep.
Hi, I think it might be already answered by your previous question, but if you only use this classification model, you don't define error bars, right? Or do you? Do you plan to have a machine learning method that define errors? If not, how would you think this could be used?
Okay, so this is our our regression model say about for the what's the actual input and what's the estimated spin. So we say some kind of the error bar we see there, right? So this is just using for this one. So maybe we haven't tried using about for the classification model onto there. So maybe we have a many bunch of the different machine learning approach to determine distance. Maybe maybe we have a more good way to determine for this one. So this is, we have a bunch of the work to do.
Thank you.
That's a good question. Other questions for the speaker? Can I steal one? How do you see, so there's, I think, a lot of progress going to happen with the next generation observations. How about the simulations? Is there more plan for that?
Yeah. So the simulation has a legacy data. It's quite, so we know at one point it's maybe the electron temperature using about for the parameterized model today. Recently, our group developing for the 2 temperature model, so we directly obtain for the electron temperature inside there. Another point is imaging using about thermal electron diffusion function, but we also consider about for the non-thermal contribution onto there. So there's some images we already extended to new data is coming to there.
Any other questions? Can I? Yep.
Based on the simulations you've done for the next generation EHT, have you already constructed simulations for that? Do you expect that, based on those simulations, to be able to recover black hole spins?
Yeah, I think it's one point. It's of course this is depend on the resolution onto there. So we see it's a higher resolution getting for the more predict the black hole spin. So in that means into the if the EHT obtain about for the 345 gigahertz image more nicely, maybe we can estimate of the black hole spin more precisely. But maybe this is asking about for the shape. It's more detail onto this.
That too, yeah.
Any last burning question? No? Okay, then let's thank our speaker.
Yeah, thank you.
Our next speaker can come up. And people, there's chairs over here. Please feel free to find a seat. Apologies to the people on the stream. I hope it's working now. Good? Okay, thank you. All right. We'll just wait for the... Okay, I can already say it. So our next speaker is Inyan Natarajan. He's going to talk about Anime JL, or do I say Anime Julia? He'll say it properly. Instrument modeling for the next generation VLBI arrays.
Thanks, Shri. Yeah, I'm Inyan Natarajan. I'm a postdoc at CFA, Harvard Smithsonian, and the Black Hole Initiative in Cambridge. And so I'm just going to talk about instrument modeling and also maybe a couple of slides on data formats for next generation radio interferometers, including VLBI arrays. Yeah, you'll all be familiar with the EHT. Just listen to Yosuke's talk. And so these are the 2 most important results that have come out of the Event Horizon Telescope in the last few years. So these were all from the 2017 EHT observations. The ring image of M87 and the ring image of Sagittarius star were published in the last 5 years or so. And we know we can see these rings with the EHT, although these black holes are like 3 orders of magnitude different in their mass and their distance. So what do you want to do next? So we want to move towards a next generation Event Horizon Telescope. So this is the EHT array as it stands now, or as it stood in 2023. And this is how it will be when the next generation EHT is complete. So have a bunch of other stations added, and you can see how the UV coverage changes and improves a lot and over multiple frequencies with the NGEHT. So the idea is to do simultaneous observations at 3 different bandwidths, 86, 230, and 345 gigahertz, and they'll have wide fractional bandwidths as well. And the UV coverage will be dense. We expect an improved dynamic range of 1,000 times. And the field of view can be expanded. We can image the jets and how the jet connects to the black hole image with the NGEHT. So there are long-term monitoring campaigns planned. And just to give an idea of how the data sizes are going to be, so you'll start with tens of petabytes of data, and which after correlation become hundreds of terabytes of data after calibration. They reduce further in dimensionality by 6 or even 8. And then in the end, all people will be interested in is a movie, which is like a few hundreds of kilobytes or like megabyte. And so this is how much the data gets reduced. And so the algorithms that process our data have to make sure that we have extracted as much information as possible. So we need flexible models for calibration to describe the variability in source and propagation path effects, including the behavior of the instrument at the frequencies that NGST will operate in. So here's a quick overview of signal propagation path. So the signal from the black hole or any astrophysical source is not just going to be uncorrupted as it reaches your telescope. So you'll have a bunch of effects like absorption from the atmosphere, emission from the atmosphere, and turbulent phase delays that can be introduced by the troposphere at these frequencies. And then you have the antenna parameters like instrumental polarization introduced by the polarization feeds. And the bandpass will introduce its own effects. And there will be time variable receiver gains and other noise components here. Plus, we need metadata, which correspond to station locations on the Earth and the observation schedule. And also, there are a priori calibration effects to be considered. So what we need are proper models of the instrument, regardless of whether you're simulating or calibrating your observations. So we would like to take a forward modeling approach. And so these are some examples of the kind of simulation and calibration software we already have and we use within the EST. So the EST imaging can perform interferometric simulation, calibration, and analysis, and final imaging of the data. And SIMBA, which uses Mexilot V2, which was developed here in South Africa, and calibrated using RPCOT, which is a CASA calibration pipeline. So it can perform end-to-end simulation and calibration. And there's also NGST Sim, which builds on top of the core functionality of EST imaging. And it introduces a few features such as simulation of fringe fitting and a bunch of site and location information. So all of these, what all of these have in common is forward modeling of instrumental effects. So not just source models. So you would have heard in Yosuke's talk about how black hole source modeling is difficult, and it's like a lot more theory oriented. So we don't need any general relativity here, but you need a lot of physics pertaining to the atmosphere and the instrument itself. So we've been trying to develop something similar in Julia, taking lessons learned from all these different simulation packages with the aim of just providing instrument models to any calibration or simulation software that is written in Julia. So one of the primary imaging packages that is now being used within the EST is Comrade, as written by Paul Tida. It's a Bayesian modeling software for VLBI, written fully in Julia. And it has sky models and instrument models. And also, these models are like natively differentiable in Julia and can be optimized. So why do we choose Julia? I don't know if you can read this. So these are some basic mathematical operations like matrix multiplication and like a few other array operations. So you can see that Julia here is as fast as newer languages like Rust or Go and comparable to C. And Python sits somewhere over here. And of course, this is mostly vanilla Python and NumPy. But you can also do JIT compilation in Python and bring the performance to a more comparable level. But then in Julia, you can do it with fewer external libraries and less effort. And there's already a lot of support for scientific computing in Julia. So this is the package that we have developed. This will serve as a testbed for a lot of things that I'm going to describe. So it's called anime.jl. It just stands for atmospheric and instrumental models in the measurement equation. So the idea is to perform upstream forward modeling as much as we can, not just model the instrument, not just model the visibilities, but also metadata related to the station parameters. And we try to build these models. We try to make this as physics-based as possible and also as statistically consistent with actual observed data and the instrumental properties. And we'd also like it to be interoperable between the different software packages that are written in Julia, mainly Comrade, which is what we are focusing on right now. And we would also like to support popular VLBI data formats existing and future. So this is registered with the Julia's general registry. Anyone can just like install it. trained by the data. And a covariance or kernel function encodes the assumptions about the function. So these are some examples of the instrument models that we currently can generate with Anime. So on the top left, you see time variable receiver gains with some adjustable characteristic time scale. So on the top, you see the phases, because you see a lot more variation in the phases, and that's how phases tend to vary if you look at actual data. And here's the variation in amplitude, which tends to be a lot more smoother over a scan, which lasts for a few minutes as far as EHT is concerned. And so these are time variable station pointing errors. This encodes like pointing offsets and the drift of the beam over a scan or an entire track. So there are long-term and short-term pointing effects that you can add. And there's also some atmospheric effects that we add. So for which we also use Gaussian processes to model these ad hoc turbulent phases that are introduced by the atmosphere. So just as an example, the red curves that you see here denote phases, and you can see how the turbulence just like goes up and down. And so these must be removed during calibration and fringe fitting before you can actually start averaging the data and trying to make sense out of the data. So I just want to talk about data formats briefly. So currently, we try to support commonly used data formats in VLBI and radio interferometry. So we have some experimental support for UV fits written by Sasha Plavin. So this is, so we don't have to go through a C layer, we don't have to go through a Python layer. You can just directly access UV fits from Julia. And we also support Casa measurement sets using a package called casaco.jl, which provides some limited support to Casa. And we are also hoping to support something like the MSV4 format, which is currently being developed by people at NRAO and a few other radio enthusiasts around the world. There's also a Python implementation that's being developed called XRadio. We would like to take the data schema and try to develop a package in Julia that's compatible with this MSV4 standard. And there's also a EHT-UV-data.jl package, which is spearheaded by Kazuo Akiyama at MIT. So it's a multi-dimensional VLBI data container. It's based on the dimensional data package, which is quite popular within Julia. And so this is probably something similar to MSV4, but they're not exactly equal. So maybe EHT-UV data will evolve to incorporate MSV4. And we would also like to explore ways for representing data at different stages of observation. So not just visibility measurements and products that we derive from visibility, like closure quantities or amplitudes and phases, but also we want to think about what we do with correlated data and how we represent it. So DiffX is a type of correlator that's used within the EHT, and there's also MK4 is a correlated data format, and these formats are not really interoperable. So we would like to have a modern data format that that's compatible with correlated data, calibrated data, and then data that's ready for imaging after some post-processing done after calibration. And also metadata, such as system temperature, the DPFU, and also gain tables that are output at every stage of calibration. So we would like to have some schema or standards for all these data formats so that right after correlation, you can just start modeling your instrument and be consistent and seamlessly move between the different stages. There's also the question of internal representation of data. There are different data formats that are amenable to different tasks. So if you want to store your data, you want data that are performant when it comes to in-memory storage, and then like for on-disk, first for on-disk, and then for in-memory, while you're working on the data, you would like data access to be as fast as possible. So there are some standards for this, and also some support in Julia, although it's still under development, but there are some basic things that you can already do. Like for example, Parquet is a columnar in-memory format. It's developed by Apache, and it can directly be queried using duckdb.jl. So as long as you have this data stored somewhere, it's just, you can just query it right away. You don't have to read it first, and you don't have to incur the IO cost. And there's also arrow.jl. So it supports any tables.jl compatible package in Julia for in-memory data processing. And there are Python implementations that exist. At least one that I'm aware of is Archie, written by Simon Pickens here at Sarajevo, which has a limited implementation of Casa core and using the arrow standard. So we would like in summary, we have been working on instrument modeling. We'd like to realistically represent underlying physics and generate large models at reduced computational cost. There are also already supporting scripts that can generate synthetic data at a much faster rate than some of the synthetic data generation software that we have in the EST right now. And we can also use this for feasibility studies and identifying new sites for expanding existing arrays or designing new arrays. And we would like these instrument models to be useful for calibration and imaging, so you can provide model priors to calibration and try and implement generalized phase calibration fringe fitting entirely in Julia, avoiding the two-language problem of having to go through C or C++ and then Python, and integrate with other existing software in the ecosystem, like Comrade and some other packages in the EST Julia environment, and then also use it as a test bed for developing some unified model for representing data. Thank you.
Thanks very much. Questions for Inian? And maybe say your name.
So I'm Michelle Lochner. Thanks so much, Inian. It was very, very cool. I have an almost sociological question for you about Julia, because of course there's been this core of people that have supported Julia for a long time and really love it, but it's very hard to shift Python. Everyone uses Python, and probably I'm not the only one who, when I see a cool package, I'm like, oh, I want to try it. Oh, it's not in Python. So it's just, what's your experience been with the kind of uptake of this package and Julia packages in general? And also, could you comment on ease of use for somebody who's never used Julia to maybe try to convince people to give it a try?
So on the ease of use side, I don't think it's as difficult as people tend to think, because you can, as Sasha was saying yesterday, I think, you can write code like Python and it works like a C code. So that's actually interesting. And I don't think learning to write basic Julia code, even code that's a bit performant, is that difficult. But I think, the uptake is, like if you already have an ecosystem that's entirely, like you depend on a bunch of Python software, and so you may want to write something in Julia, but the associated, like the software packages that your software depends on is all written in Python, and there's not enough Julia support. It does take time, and you need like a few interested people and funding to do something like that. But I still use Python, so I do a lot of calibration stuff. The software is written in Python, so sometimes like during daytime I'm working in Python, and the evenings I'm trying to develop this, and then I keep making mistakes I shouldn't be making. So yeah, it does take time, but I think but there are a lot of so since we all tend to do a lot of scientific computing, there's already a lot of support for this, and I don't think it'll be that difficult for, if there are like 2 or 3 people in your group who want to explore it, should probably let them. It'd be cool.
Thanks, Inian. Other questions? Jordan.
Yeah, thanks for a great talk. There was quite a bit of overlap with some of the things we're starting to think about within the Australian SKA Regional Centre, like collating of large data, the data formats, and essentially making sure we're ready for the onslaught of data from the SKA. One thing in particular I'd like to think about is kind of simulating the very large data rates. So I was interested to know from your data flow, what scale of data are you able to simulate, and at which stage is it coming in? Is it the post-correlation data onwards?
I haven't tried to simulate any data set that's more than maybe a few gigabytes. It's usually like a few hundreds of megabytes or something like that. So it's not really a big data, at least as far as EST, as far as EST specific simulations are concerned. But yeah, I'm not really working on like connected element interferometry as of now. So it's probably something that I personally will worry a bit down the line.
Okay, thanks very much, Inian. We'll move on now. Thank you. All right, we have an invited talk next from Tathanka Roy Chowdhury. He'll be telling us about exploring the high redshift universe using SKA and other upcoming observational facilities. Just wait for the switch over. And I'll give 5 minutes. You can maybe start introducing yourself. Okay, super.
Okay. Okay, let me anyway start. Let me start by thanking the organizers for the invitation. So I will be talking about something different from what you have been hearing so far. So this is about the high redshift universe using a variety of observational facilities. So let me actually first set the context of what I'm going to talk about in this talk. So if you think about our universe, the way the large-scale structures evolve, they originate at some point, we don't understand, but the first indications of the fact that our universe is not completely smooth is found when the universe is around 400,000 years old, the corresponding redshifts being of the order of 1100, we see these small fluctuations, which is probed through CMB. We also observe the universe locally at relatively low redshifts, I mean, compared to the scale of the universe. So let's say from redshift 0 to about redshift 6, 7, 8, through various galaxy surveys. There is a phase of the universe that is still unexplored observationally, so that is this gray region. So it's by itself a very interesting job to go make instruments and try to see what's going on here. What interests many of us is the fact that somewhere in this gray area, the first stars, the first luminous sources, the first galaxies in our universe would have formed. And one would like to understand how they look like, what their nature was, and how they kind of affected the later part of the evolution. So the search for the first stars is actually a very relevant and very active field of research. There are a variety of observations being ongoing and being planned. For example, we've all heard about JWST, which is already giving fantastic results. And then there will be various like next generation of ground-based telescopes, which will be coming up later in the decade or early next decade. JWST, in fact, is already kind of breaking records. So this is a plot from a paper in the last year. This plot has already been updated, but the basic theme remains. What has been plotted here are, I mean, each of these markers are basically galaxies. So the x-axis is the redshift. This one is the observed flux increasing this way. The points you see by these crosses are basically the points, the galaxies we had access to before the JWST came up. That would be the HST data. And all these other symbols, mainly the diamond ones, are basically JWST data. So you can clearly see that this part, the high redshift part, is getting populated and getting populated very fast the moment JWST has started observing. And we are kind of reaching redshifts of the order of 15, 16 now. I mean, these to make simple models to see what the corresponding data tell us. So what has been plotted here is the galaxy luminosity function. So basically the number of galaxies versus their luminosity. And the points with error bars are the data that are essentially coming from JWST, and these are coming from some model which we have constructed. The point is, the fact that these models, after tuning the parameters, match this data is fine, but what do they tell us? For example, if we plot something which I call the star forming efficiency, how efficient are the galaxies in forming stars, the models tend to give these lines. And what you can see is, up to redshift 10 or so, the model was kind of consistent with something that is constant. So one would have thought that the galaxies would be, the physics of the galaxy formation would be similar at these redshifts. But by the time you hit higher redshifts, it seems that the data, although there is quite a bit of uncertainty, the data is demanding a rise in this quantity. So we need in some way to the efficiency of star formation to go higher at high redshifts. Now there are already several explanations in the literature, but with the kind of models we are doing, it's not very easy to break the degeneracy between these different kind of explanations. And currently we are trying to see if we can use more data to figure out whether which of these or if something else indeed is true. But moving on, this is one way of probing the high redshift galaxy, that is a high redshift universe, that is through direct observations of these early galaxies. But then there will always be what we call this luminosity bias. You will always be kind of biased towards the bright galaxies. So you always have this doubt that are we reading too much into these data from only a few kind of relatively bright galaxies. So it is always good to have complementary methods, and one such method is to use hydrogen. So essentially the basic idea here is that as you form galaxies, so these are basically snapshots from simulations. So this is a cosmological density field, and white regions are places where we expect the galaxies to form. The ionizing radiation from these galaxies will come out and will start ionizing the surrounding hydrogen. So if you plot a map of neutral hydrogen, you will find that the regions around the galaxies are preferentially ionized, whereas regions away from the galaxies toward the voids are preferentially neutral. And this is a time evolving picture. As more and more galaxies form, as more and more ionizing radiation are thrown into the medium, these black regions will kind of grow, they merge, they overlap, and eventually the universe gets completely ionized. And our current understanding is this completion happens somewhere around redshift 6, slightly less than 6 or so. The importance of this process, which is called reionization, is immense. Studying this reionization will tell us about galaxy formation. They will also tell us about cosmology, because they are really directly related to the formation of the first cosmological structures in our universe. You can even start, probably we can also study non-standard extensions to the lambda CDM and exotic dark matter and so on. Now this reionization, how do you probe observationally? You actually use a variety of probes. So the first one, which is actually the first one to tell us that the universe was reionized, are what the absorption spectra of quasars, distant quasars, through what is known as the Gunn-Peterson effect. So what happens is you see these absorption features in the quasar spectra, and they are arising because of Lyman alpha transition of neutral hydrogen. So these regions are called Lyman alpha forest. And by the time you have hit redshift 6, you will see this part, there is a strong absorption, probably indicating that we are approaching a regime where the universe is very highly neutral. The other observational probe, which is equally important, is CMB. So the Lyman alpha absorption probe probes the neutral part of the universe, whereas CMB probes the ionizing part. So what happens is CMB photons, as they free stream to us, get scattered of the free electrons that are produced by this reionization, and they have signatures in the CMB. And what has been very useful is that these free electrons, the scattering produces a remarkable large-scale polarization signal, which has been detected first by WMAP and more recently by Planck, and that again tells us about when reionization would have occurred. And again, from these observations, very simplistically speaking, we think that the 50% reionization, if you think about that, would be somewhere around redshifts of 7 to 7.5. So you can already see we have some idea that reionization is complete somewhere around 5.5 or 6 redshifts, whereas it's 50% ionized somewhere around 7 to 7.5. So it might have started somewhat early and then grew gradually and so on. There also exist various other probes of reionization, the high redshift galaxies, the Lyman alpha emitters, the temperature of the intergalactic medium. And then in the future, we are expecting this field to be revolutionized by the 21 centimeter experiments which are being planned. So in fact, there are already quite a bit of observational efforts that's going on to detect this 21 centimeter signal. So there is a set of experiments which are smaller in size, probably less expensive, which are trying to detect the globally average signal. And by the way, this list is completely non-exhaustive. There are various other experiments as well. And then there are experiments which consist of radio arrays. I mean, there are arrays of telescopes. These are somewhat large structures in some sense. The idea is to probe the fluctuations in this signal. So all these bubbles forming and growing and so on will probably be done by this picture will probably be captured by these experiments. And here I wanted to highlight a few. The GMRT, this is the place where I work. I mean, we are the institute that built and maintains this telescope. And of course, MeerKAT, which is in South Africa, again giving fantastic results. Of course, probably the reionization which we are after is probably not going to get detected by the existing telescopes. So we have to wait for the next generation of interferometers, in particular SK-Low coming up in South Africa. And there is a plan which is HERA, which will again come in South Africa. Now, if I go into the physics of reionization, it's again, I mean, there's a lot of physics which goes into understanding what's going on. You have to understand how the underlying cosmological density fields grow and evolve, and where the dark matter halos form, because that's where the galaxies will eventually be forming. After that, you need to know a bit about galaxy formation and star formation, how the stellar spectra kind of what their shapes are, and how these photons, if produced within the galaxy, escape to the surrounding intergalactic medium so that they can ionize. And then if they escape from the galaxy, so you have all these ionizing photons into the intergalactic medium, how do they actually propagate through the intergalactic medium? So different of these areas are studied differently. For example, if you want to study the cosmological density field and halo formation, you would probably want to do it using n-body or hydrodynamical simulations. The galaxy and star formation part, that is in cosmological simulations, it's impossible to resolve star formation from first principles. So they are usually typically done by putting in prescription, some physical prescription, something which we know from other studies is basically put into these simulations. And then finally, if you want to do radiative transfer, that is another set of numerical calculations you have to do. They are popularly known as the radiative transfer simulations. And not only that, once you have this physics put in and you build a model, you should be able to actually calculate the observables to compare your model with the data and do statistics to make parameter inference, model selection, and so on. So there are several challenges in building these models. First of all, I mean, when you build these models, you have to make sure that these models can predict different observables so that you can match different data sets simultaneously. So I have listed some of the challenges which I think are important. So I have listed them as high dynamic range, radiative transfer, and parameter inference. So let me spend some time describing what they are. First is that when you try to make these n-body or hydro simulations to capture the underlying density field and then the halos, you really need the simulations to be of high dynamic range. For example, on the one end, if you think about SK-like surveys, you would like the simulations to have volumes of the order of 200 co-moving megaparsecs. Whereas at the same time, you want to resolve small structures. For example, the small halos where the first galaxies would have formed. So this will require your kind of simulations to have somewhere around the order of 10 to the 11 what we call particles, fluid part. Yeah. Now this is of course very challenging. There are several simulations which have already been done, and they're trying to do these things as neatly as possible, but this is really challenging. People also try to find out various prescriptions to deal with this, for example, something to do with subgrid prescriptions, or try to make hybrid simulations using low resolution and small high resolution volumes. The second challenge is to do radiative transfer. As you all know, radiative transfer is a high dimensional partial differential equation, very difficult to solve. So you probably need some way to make this problem tractable. There are various methods to do that. One is to use the method of characteristics. So you basically convert this equation into kind of light rays, to keep it, say it simplistically, and then trace how these rays are moving as they pass through the intergalactic medium. Else you take moments of the radiative transfer equation. Of course, these moment equations will keep on growing, so you have to find a way to close them. So at some point you have to make some assumption, and they are known as closure relations. And there are again various groups which are trying to do these. A complementary method which have come up in recent times is the semi-numerical methods, where you actually don't try to solve the full equation in its full glory, but rather you say that I am only interested in some ionization field, I want to just track the ionization front, so because I'm studying reionization. So you replace the radiative transfer by simple photon counting algorithms. Okay? So that can be done much more efficiently. And the third challenge is parameter inference. Assuming you have all these models in place, there's a lot of things which are unknown in the high redshift universe. So your model will have several unknown parameters. So basically you then need to do find a way to do parameter inference, and if the number of parameters is large, this becomes a challenging problem, particularly because when the parameter space is extremely high dimension, the standard Bayesian methods take a lot of time to converge. So you have to run the models or the simulations like 100,000 to million times, and that's not very easy. So in this area, the machine learning methods have started to become useful already, and they have been used in different ways. Assuming that you want to keep the Bayesian flavor intact, one way is to use emulators. Basically, you run the simulations at some pre-prescribed kind of predetermined parameter values, and for all the other parameter values, you find a way to interpolate. Okay? So that's emulation. There is also progress in doing what is known as simulation-based inference, where you actually don't prescribe a likelihood, rather the method basically tells you implicitly what the likelihood would be, and then the claim is that these methods would require less number of model evaluations than the conventional ones, but still there are challenges. I think we are still in very early days in these. So I will spend the last few minutes telling you about some things we have been working on. We have been working on basically the semi-numerical version of radiative transfer. So these codes are kind of approximate, but quite efficient. So these semi-numerical codes have been developed over years by various groups. Many of them, the ones which are based on what are known as excursion set formalism, have a problem which was known from the beginning, that is a photon non-conservation, and that leads to several other problems. So we have been developing a code which is kind of what we call explicitly photon conserving, and that solves several other issues with the existing semi-numerical simulation. So our simulation is called script, and it is quite efficient. It can be used for parameter space exploration. And some of the results which we have already obtained are shown here. So this shows the reionization history obtained from our model. So what has been plotted here is the ionized fraction versus redshift. So at early times, the ionization fraction is 0 and it hits 1 at some point. And the red points are coming from comparing the model with CMB data. The blue ones are coming from comparing our model with the Lyman alpha absorption data, that's the quasar spectra data. And you can see if we can combine these two data sets and run our model, this space will be kind of much more constrained than what it's looking now. But I mean, at least the model which we have been working on looks, it's saying that the reionization is probably driven by faint galaxies, the small galaxies at early times, and they are regulated by feedback. And we prefer kind of extended reionization models. It's not like an instantaneous process. It starts quite early and it takes time to complete. And then we go ahead and try to match our model with several other observations like the luminosity function of galaxies, the temperature measurements, and each of them actually makes the model more and more constraining. And then CMB, what we call the kinetic Soner-Zoldevich signal. Not only that, you can go ahead and start making forecasts for the SK where there is no data, but you should be able to see how SK will do once it comes up. We are also using our model to understand these machine learning techniques, in particular the emulators. So our thing is to not to go ahead and just use emulators for parameter inference, rather you develop emulators, and wherever you can, you run the full parameter inference techniques and run one with the emulators and make sure they are giving similar results. And they do. It turns out that the emulators we have been working on, you can get the same results with 10 times less computing resources. So that is already looking useful. But you have to do a lot of preliminary work to get there. And in the future, we want to actually do use like cross-correlate these different observables which we have and see whether we can learn more about reionization. So that brings me to the last slide. Basically, I want to summarize what I have been telling you so far. So the first stars and the high redshift universe can be studied using reionization of hydrogen, which will be complementary to the direct detections you have from the JWST. And modeling reionization as well as parameter inference would require detailed, but at the same time efficient simulations. And I have highlighted our effort in this direction. That's a semi-numerical simulations called SCRIPT. And as you would have appreciated, that constraining reionization requires simultaneous use of different data sets. And we already have interesting constraints with the available data, but we think that with the SK era kind of very near, it will really tell us how reionization progress, but we need more accurate and fast numerical simulations to interpret the data. So I will stop here. Thank you very much.
Thank you very much. Questions? Anybody? Very clear talk. Oh, sorry. And please say your name.
Hello. Hi, nice talk. So related to parameter estimation and thinking about SKLO, are there plans to combine all that multi-parameter estimation with possible instrumental effects, which we all know will be very problematic with this type of interferometer? So in a full form modeling approach, is that possible?
Yes, to some extent, people have already been trying. I mean, so with simplistic foreground avoidance techniques, I mean, one has already started to put these things into the parameter estimations, and that's where, again, some of these machine learning techniques help. And that is already telling us that the kind of forecasts we had made earlier, they were somewhat optimistic. You won't really get the large scales so well because the foregrounds are taking them away. What has been missing, I think, is the real instrumental systematics. I mean, foregrounds are still being modeled in idealistic sense and so on, but that what the instruments will do is still something not being done very rigorously, and that's something or I would say they are being done, but they are not being then coupled with the reionization models very realistically. So that's the part that's still missing, I think. So yeah, there's still some work to do there.
Hi. So from the simulation side, you have the production rate of stars that are in the early universe that are generating UV photons, and then you have the coupling efficiency between the UV photons that are being generated by those stars and the surrounding medium. So there's a bit of a degeneracy between those two things on the simulation side. Do you think you can comment on, until we actually observe things and make constraints on how many stars we have in the early universe, can you comment on how simulators can make efforts into breaking this degeneracy?
Yes. So yeah, so that is the thing. So there are several degeneracies in the way these models are built. So you of course have to know how the stars were formed and what are the UV luminosity, how much UV luminosity they are producing. That probably you can constrain using the UV luminosity function. But the next step from going to UV luminosity function to the ionizing photons, number one, that is intrinsic spectra of the galaxies. And number two, how many of these ionizing photons will come out from the galaxy to the surrounding medium, that's the escape fraction. So what happens is in reionization models, all these components come together and you can constrain only one parameter, which is a combination of both. If you have UV luminosity function, you can probably turn it around and try to constrain what would be the escape fraction of galaxies. So using reionization and other things. From the modeling side, if you try to model, for example, escape of photons from the galaxies, that is extremely challenging. I don't think we still even understand what is the main physics which drives the escape of photons. Is it the structure of the gas in the galaxy? I mean, where they form channels and the galaxies can escape? Or is it some feedback process? I mean, if you blow some gas because of some supernova explosion, that helps the photons to escape and so on. So there is still a lot of ideas in the literature and people are working on them, but we haven't reached a phase where we can model this escape part very rigorously.
Other questions? We have time for one quick one, if anyone's burning. I mean, I have one. What do you think is the main challenge that's faced? Is it the lack of, so you mentioned, our lack of physical understanding? Are we going to need huge computing resources to make the models? So I'm a simulation person, so my question is always about simulations. Like what do you think is it, which one do we need more?
Yes, okay. In principle, yes. I mean, if you get more computing power, you can probably solve some of the equations from like more first principle point of view. But I don't think that is the way one should progress. It's going to take a lot of time. So I think there is no new physics involved. It's just too complex nonlinear physics which is going in. So you need smarter ways to kind of solve these equations. So there is still some scope of doing, I don't know, approximation, analytical studies, and then put into the simulation.
So you think it's more like coming up with smart algorithm, like analytics, rather than like putting because I would brute force, put all the physics in it. They just run it with big simulation and you get your answer.
That is my personal biased opinion. Yes, you do a bit of analytic approximation, try to probably develop a few more numerical techniques which are useful, and then give it to the computer. They will do the rest.
Yeah, super. Okay, let's thank our speaker again and our last speaker. Thank you. So we've gone from EHT to some SKA, and now our last speaker is going to talk about visualization. We have Lucia Marchetti, and I hope, there we go, it's coming. And she'll tell us about scientific exploration of spectral cubes and particles using immersive technology, Davy, paving the way to the SKA. I'll give you a 2-minute warning.
Thanks, yeah. So hi everyone, thanks for giving me the opportunity to talk about this in this meeting. It's a little bit of a shift from what you heard this morning, but I hope you will enjoy anyway. And from this slide already you can tell that what we are developing at IDEA, which you're going to hear more about during this meeting, is not only a tool for visualizing astronomical data set, but actually something that can be applied in any type of data cube actually that you want to, so including simulations and others that you heard. So that is actually an MRI of a human brain, and you can actually use our software to do that. Okay, so I'm going to talk about, sorry, just to mention, so I'm Lucia, I'm the director of the Idea Visualization Lab. These other people here at the bottom are really contributing to the development of the software, so, and some of them are online, so if you have questions, please don't hesitate. So we are a unit of the Inter-University Institute for Data Intensive Astronomy here in Cape Town. And Rob is going to talk a bit more about the computing side. So I'm going to just focus on the actual physical space that we have to experiment with visualization. As you can tell from this slide, we are a space where we experiment with different means, and we try to break them, basically, bring them to the point that we test what actually is useful for the new data that we need to analyze. So why we are doing that, especially looking into the virtual reality space now, because we are really at the moment in which we are dealing with a lot of data cube coming from our, marvelous radio telescope. As you can see from the top, if you're a radio astronomer, you know what I'm showing you is a data cube. We usually investigate the data cube through, slice by slice, but what if you could actually see everything, in one go? And this really enables you to start seeing things that you have never seen before, connection between filaments of galaxies. And as you can tell from these, you can already see that the 2D plot that you have on the bottom right is immediately seen in the video that we shoot with IDAVI. So IDAVI stands for Immersive Data Visualization Interactive Explorer, big name. I'm not going to go into the details of these slides. You can ask me how we did it. But is available for everyone later on. And the IDAVI requirements doesn't need too much to run. We actually have it at the booth here, and bottom line, you can run it with nothing too fancy, okay? But these are some of the specs that we recommend. So what does it look like? So if you are on a computer, you load your data. This is our desktop interface. But the more important part is where you are in VR. You start to see your data cube. This is actually a Meerkat observation of Fornax galaxy. So you see that is the cube that is in front of you. You have all sorts of analytics that we have implemented in it. But more importantly, this is how you swim in the data. So you immerse yourself in the data set. You start to see if there is connection between galaxies, and you downsample. We downsample big data sets so we can actually visualize big data set, but then as you crop to the region of interest that you are looking perhaps at a specific region, then we go down to the higher resolution and we analyze that in detail. We have all sorts of different things implemented already. You can paint your own mask. I know that identifying H1 sources can be tricky sometimes. So we have implemented something that you can just go in VR and, okay, this is my galaxy, this is true, and this is actually what is not true, and we can delete it from a mask that has been maybe originated from Sophia or other algorithm. Analytics, moment 1 and moment 0 are also available within. You can also extract them, download them, so it's very effective to actually give you data like science-ready plots that you can include directly from the VR space into a publication, which we are really proud of. We also have the ability to overplot a Redshift catalog, for example, or any other catalog, actually, if you want. So that should also help you to find new things inside the cube, digging into the noise, and you can play around. You can say, okay, I find all these galaxies running my algorithm. Let's take that out and look to the residual and dig into the noise to find new things. So many, many things are available already. So we have had a series of releases already, beta releases, and I have to mention that IDAVI has also seen a contribution from INEF in Italy, who actually helped us to develop some of the GUI that you can use. But we are ready for our very first data release, including the source code, which is going to be publicly available, and we hope to increase the contribution for the community by doing that. So please come to the booth and stop by if you want to know more about this. We had a series of publications actually using IDAVI successfully. I mean, apart from our team publications, at the bottom you see a list of some of the papers that have used IDAVI to actually find their science. And if you use the QR code there, that is actually bringing you to a series of publication lists. So these are just some highlights. And I'm going to give you some examples. So I'm happy that Nathan is here. So this comes from his paper, where we actually discovered this possibly, ring galaxy. And IAU was instrumental really to analyze this object. Any automatic source finding was actually failing to identify the structure of this galaxy. And so with our software, we have been able to isolate the source in the middle, the ring around, and study that in detail, so studying the content and the velocity fields of this H1 gas. Another one was recently the discovery of the 49er by Marcin Glowacki, who used IAU to confirm very quickly the discovery of these new 49 galaxies that in H1 is a big number, okay? And this was only done with a few hours of observation with Meerkat and few hours analysis in VR. So this is just a shot of what is the cube. We have other work in progress, and IAU is really good when you have complex system to deal with. So in this case, we have a merging of galaxies, and it's quite complicated. When you look to the cube, there is a lot going on, and isolating all these different features, it's very complicated if you don't do it basically by hand inside the cube. So these are the different flavors that we have. We have the volume rendering, but we also have particle, and we have a project for bringing the VR to the dome as well. So if you are a fan of planetarium, also talk to us because we have a prototype that works with that, but also multi-parameter space catalog, okay? So if you have a simulation, for example, you want to visualize that and go inside and see the particle rendering of your different gases, you can do that in VR as well. And I know Neil Katz from UMass actually have used our IAU to look into his simulation, and he was surprised because when he was digging into the data, the particle, he actually discovered a ring galaxy, and he didn't know that his simulation could actually generate ring galaxies. So I said, oh, look at that. So, I think it's very useful for a lot of things, and it's becoming more and more useful. This is an example of the particle rendering, look into multi-parameters connection. This is actually a study that we did with a previous version of the software, but still useful, in which we are actually looking to the clustering properties of galaxies, and the different line with different colors tells you how likely it is that these galaxies are in pairs in the space. And this is using the 2MRAS survey. And this is another example of the cosmological simulation that you can actually see in our booth. But what's next? So we are dealing with big data, right? So right now, in a sense, our software is limited to the capacity that the computer that you have can run and load, but we are looking into streaming VR, which is a new field completely, and we have to create it basically on our own. So we do have already tried local streaming at POSI. So POSI is actually running our own software in their supercomputer. So if you have an account there, you can actually log in, and what you will see is our software running streaming. The problem is that you can only do it in a local environment, meaning a few kilometers away from the server, because the data frame is not enough otherwise, and you would get sick. I mean, the motion sickness in VR is going to be important. So we are actually investigating how to do it more efficiently on a longer distance, using what we know about, streaming big data into the cloud, using what we have done at IDEA developing Kata, which I'm sure you're familiar with. If not, come and talk to us, but this is basically the reference for big data in the cloud analysis that is now running for ALMA as well center. So this is our framework, and we would like to use that to then stream VR. So we are going to use a similar approach, and we have a prototype now that Rob and a student developed already. We just need to develop a little bit more to actually be fully integrated. And the idea is to go from the lower resolution that you can grab from the data, stream only the data that you need to see, and then be able to upscale when you are in VR, so that you don't have that problem of data frame, as we said. So we are getting there, and this is going to be very important when we actually going through the regional center for the SKA, possibly, because this would be a very important tool to be deployed in every regional center. And closing down, I would like to give a mention to Tom Jarrett, who unfortunately was our director till last year, but who passed away on the 1st of July. He was supposed to be here for the big release, and unfortunately, he's not. So I wanted to give him a tribute here, because, yeah, of course, it was part of the team. Last announcement, we are actually, I mean, if you have your own data, you can actually come to our booth. You can scan that QR code and you can book your own session with us. If you want to bring your own data, we are more than happy to try it out. And I challenge you to break our software. We really need that so that we can test any bug before we actually release it. So please come and talk to us at the IDEA booth. And if you have any questions, I'm here for them. Thank you.
Thanks for that lovely talk. Questions for Lucia?
Thank you for a very lovely talk. Actually, I just want to understand whether your visualization software can take up hybrid simulations in the sense like you can have fluid simulations, particle simulations, and so on with different kind of databases. Would that be incorporated easily or difficult?
We are not there yet.
Okay.
We have a long list of things that we would like to implement, and we are, right now, I would say that we have prototype of trying out for the simulation, but it's not fully fledged for that yet. What we are going to release is a software that is going to be very useful for H1 or spectral line cube analysis right now, and all the rest is coming. Okay. So bear with us, but we are more than happy to receive feedback from the simulation community because we need to know what you need to see to make it happen, basically.
I've scanned the code.
Thank you.
Thanks.
Go ahead. Go ahead.
Hi, that was,
Hi.
sorry, that's super cool.
Thank you.
So have you, I mean, maybe you already, maybe that was the answer to my question, but I was thinking there's all sorts of other multi-parameter data sets. There's Sloan, there's DES, there's,
yeah.
Gaia. So, I mean, how flexible is this? I mean, could you put in like any 3D data and play with it? I mean, 3D, and it doesn't have to be even like in positional space, right? It could be
any sort, yeah. So if we go back, this is very important actually, thanks for asking. So the particle render is really a multi-parameter thing. So you can think of visualizing. So the volume is a thing, right? We have the voxel, and that is the volumetric rendering.
Right, yep.
Then if you go to visualizing catalog like SDSS, Gaia, all these other things, right? You have either the position and the redshift, but you can start to play around with any possible correlation. And you can, anything that can be encoded in shape, color, and space, basically. Yeah, and dimension as well. So you can have, I would say, 5 parameters at a time, easily visualize and start to see correlation between the things. So for example, if you think about the very famous specific star formation rate, the main sequence of galaxies,
right.
If you plot that into a 3D space and you plot it against the H1 mass, you see that main sequence is actually a plane, right? As a so these kind of new things can be explored, and the only things that we have now is input format. So we are working with VO table, FITS file, any format that is usually used in astronomy.
Yeah, I mean, for me, the obvious one was like from Gaia, like proper motion array, proper motion distance, right? And just look at it, and just look at those 3 dimensions that way.
Yes. No, we can.
Yeah. Cool. Well, that's awesome. All right, thanks.
Thanks. No, but I'm happy to chat more.
Yeah, good. I will definitely come by.
Okay.
Any last question? All right, then we'll thank Lucia and thank all the speakers from the session. Thank you all very much. And it's time for lunch, and we'll see you back for the next session after lunch. 1:30.
Yes, exactly. It could be worse. It could be worse.
Are you oh my gosh. Are you able to hear us, Gordian? You can unmute yourself.
Yes, I can hear you just fine.
Okay. And then we
Loud
want
and
to
clear.
test if we can hear you in the room.
Yes, does it work? Can you hear me?
Can
Hi,
you speak again?
yes, can you hear me? 1, 2, 3, 4, 5. Can you hear me? Um, okay. Zoom says that I'm talking, right? But can you hear me?
I can hear you from online, but I don't hear a response from out there.
Okay, then I guess they have still some sound
Are you able to
issues.
share your slides, Gordian?
I hope so.
Oh,
I think the screen sharing just worked, right? Did you see, or can you see the screen now?
okay, we can see the screen now and we can hear you at the same time. Are you
Okay,
planning to
perfect.
have your video camera on?
Yes, I can test it in just 1 second, or I can test it right now.
Okay,
Can you
super.
see me as well?
And I see you and the light is good and everything is good. We're not looking up your nostrils or anything crazy like that. So good. All right, super.
Perfect, thank you very much.
All right, we'll talk to you later. Bye.
Thank you.
when we're dancing close together, wrapped up in our bliss. My heart is racing and anticipating the magic in your kiss. We share a special feeling. I hope the music never ends. With you, love takes on new meaning. Girl, let's move across the floor again. You make me shiver. Girl, your love is such a sweet sensation. Oh, you make me shiver. Baby, when you're here with me, it's fascination. Come on, take me, I'm ready.
Welcome back, everyone. So we start the second session of our focus meeting. So we have 5 talks. The first one is an invited talk, and then we have 4 contributed talks. So may I welcome Dr. Michelle Lochner to present on enabling new discoveries with machine learning.
Okay, thank you very much. Cool. All right, well, let me start by thanking Shazreen and the other organizers for inviting me to give a talk at this session. It's pretty phenomenal to finally be at the GA in Cape Town. So I'm Michelle Lochner. I'm a senior lecturer at the University of the Western Cape. That makes me a local. And I'm also a staff scientist at the South African Radio Astronomy Observatory. And I'm going to be talking to you today about how we can use machine learning to make new discoveries in astronomical data sets. So I want to set the stage by talking about 2 instruments that I'm very excited about. The first is the Vera C. Rubin Observatory, and this is an optical telescope under construction in Chile. We should be seeing first light sometime later this year. And this is a truly incredible machine. It's got the world's biggest camera on it. It's got an incredible field of view, and it basically means it's going to be able to take a movie of a large chunk of the southern sky. And what this means for science, if you can watch this video, this is every supernova discovered since the 1800s. Watch closely because it accelerates very, very quickly in the last few years. And you'll also notice the graph on the right, you're starting to see more and more and more supernovae that are not spectroscopically confirmed. Yeah, it's kind of ridiculous. And we're up to about 70,000. We'll easily have over 1 million by the end of the survey being taken with Rubin. And if you look at the graph, you'll see we're starting to get more and more supernovae that are not spectroscopically confirmed. So if your background is cosmology like mine is, we only care about the 1As, we're not going to know which ones are 1As. And this is a field that machine learning is absolutely critical for trying to distinguish between these different types of transients. So let's do some numbers. How much data are we really talking about with Rubin? If you just imagine for a second and think to yourself, make a guess, how many galaxies are going to be in the final catalog? If the number you came up with was 20 billion, you'd be right. Now take a guess. Every single night, Rubin is going to detect things changing on the sky, and it's going to issue alerts. So take a guess how many times a night something is going to change. If you guessed 10 million times a night, you'd be right. So this is the kind of volume of data that we're having to figure out how to deal with. All right, let me talk about another telescope that I'm super excited about. All South Africans are very excited about this, and Australians and many people all around the world. That is the Square Kilometre Array. So this will be the biggest telescope in the world, and it's under construction jointly in South Africa and Australia. And the data rates from the SKA are nothing short of stupid. We're just talking about petabytes a day of raw data, and even the processed data, we're also talking about billions of galaxies, millions of candidate pulsars and FRBs, and other transient sources. So it's even more overwhelming. But we don't even have to wait for the SKA to be built. And by the way, the first dish has gone up out in the Karoo in South Africa, but we don't have to wait because we already have beautiful precursor telescopes that are starting to push how we do science. The first one I want to mention, of course, very close to my heart is Meerkat.
So this is a radio telescope out in the Karoo in South Africa, absolutely beautiful data. And it's already, you know, radio astronomers are used to being able to download their data and just kind of play with it on their laptop. A very simple, ordinary observation with Meerkat is easily a terabyte, right? So we're already doing things a little differently. Of course, our sister instrument, ASCAP in Australia, is taking these incredible surveys, generating enormous volumes of data, making new discoveries. And we have the same sort of thing going on in Europe with LOFAR in the lower frequency end. So these telescopes and other precursor telescopes represent kind of a step change in radio astronomy from how things were to the modern era leading towards the SKA. So basically, I feel like this. The amount of data coming out, it's beautiful, it's exciting. The opportunity for discovery in particular is just immense, but it's also overwhelming. And this is why machine learning is becoming more and more popular to try to handle the problems that we're dealing with this data. So I want to talk specifically about anomaly detection. I think everybody has a pretty good intrinsic idea of what I mean when I say anomaly. An anomaly is anything that's different from the norm, unusual, rare. And we already have some good examples of these in the known unknowns. So these are things like strong lenses or gravitational waves or fast radio bursts, although maybe these are less and less anomalous these days. But these are things that we know about, they are rare. So there's usually very little training data. It's difficult to build machine learning algorithms to go and look for them. So that's why you might want to use anomaly detection to try to pick out these things. And they're, of course, scientifically interesting in their own right. But I don't know about you, I get out of bed every morning and do science because of the unknown unknowns, the unexpected discoveries, the things that we weren't looking for. My favorite example of this is the 1967 pulsar discovery by Jocelyn Bell Burnell. And the thing is that what it took to make this absolutely groundbreaking discovery was a very bright graduate student carefully looking through all of her data and noticing something weird. So the question that's been kind of hounding me for the past few years is, how do we make these unexpected discoveries when there are 10 million alerts a night? When there's 20 billion galaxies in a catalog? When there's just not enough grad students in the world to look through all of your data? And this is where I think machine learning can play a really critical role. So there are machine learning algorithms to do anomaly detection. They're very different from the types of machine learning that most people have come across. Most of those are called supervised learning, where you have a training set and you train an algorithm to perform a specific task, like classification. You can't do that with anomaly detection because by definition, you don't have training data for things you've never seen before. So these algorithms work more or less, you throw a whole lot of data at it, they try to kind of learn what normal is, and then things that are far away from norm are deemed to be anomalous. Some examples of these are like isolation forest, which is based on the very popular random forest algorithm, or local outlier factor, which is a density-based algorithm. But this is not really the main point that I want to make. When I started working on this a few years ago with my collaborator, Bruce Bassett, we realized really early on that anomaly detection alone is not actually enough, because anomalous does not equal interesting. So for example, for me as a scientist, I'm not particularly interested in artifacts. They might be anomalous, they might be rare, but they're not very interesting. I might be interested in more real sources. But a different scientist might find different types of sources interesting. And somebody who's in charge of the data quality pipeline might actually really care about the artifacts because it means something's wrong with the pipeline. So what's anomalous might be fairly easy to define, but what's interesting is subjective. And it's really, really important that we make this distinction and that we incorporate this idea of interestingness when we want to do anomaly detection. This is where active learning plays a really critical role. So active learning combines the raw processing power of machine learning with the knowledge and intuition and experience of a human user. And the goal with active learning is to solve some particular problem with the absolute minimal amount of human intervention, so the minimal amount of labeling, etc. So if you put all these pieces together, you get astronomy. It's a great name. Nobody knows how to spell or say it, but if you Google it, you'll get to the right thing. So Astronomaly is a general purpose framework that Bruce and I built for anomaly detection in astronomy. It can take basically any kind of data. The back end is Python. It can take images of whatever wavelength, time series data, spectra, whatever you want. It performs this very important step called feature extraction. In my opinion, this is the hardest step of any machine learning problem. You have to take something complicated and high dimensional like an image and simplify it down into a meaningful set of numbers that your machine learning algorithm is able to actually deal with. This is really difficult, and this held the field back for a very long time until deep learning came along, which I'm about to talk about. Once you've got your features, those lower dimensional sets of numbers, you can do anomaly detection, and then what's very important is this loop. So I built a JavaScript front end that allows you to basically give a score for the different objects in your data set on how interesting it is. So this turns a very binary kind of yes-no anomaly problem into something a bit more nuanced. It allows you to get an idea of a scale of interestingness for you as the user. What will happen is that you can improve this anomaly detection algorithm to get rid of the stuff it knows that you're not interested in, like artifacts, and focus on the things that you are interested in. Ultimately, Astronomaly is kind of a recommendation engine for interesting sources in astronomy. So it's a little bit like if you're on Netflix or YouTube and it tries to recommend videos it thinks that you're gonna like. We do the same sort of thing, but for anomalies. It's publicly available. I really encourage you to play around with it with your data and give me a shout if you need any help. This is just an example of it in action where I labeled these sources, or I gave them very low scores. And then as you go through more labeled examples, you don't see too many of the boring things that I've told it are boring, and you start seeing more and more of the interesting stuff that can focus on what you as a user find interesting. Okay, remember I said that feature extraction step is the most important and the most difficult. When I did this work, the original paper, I used some very simple features that describe the morphology of the galaxy. Really just like fitting ellipses to isophotes, very simple. And it does okay, but it doesn't do very well at very nuanced, slight differences between galaxies. And it's really deep learning that has driven the machine learning revolution. And we wanted to make use of the deep learning tools available. So deep learning is a branch of machine learning where you use very deep neural networks to solve problems. The thing that most people don't realize when we talk about deep learning is that if you take, for example, this is a very typical convolutional neural network. It's called a ResNet. It's very complicated. You've got all these layers and neurons connected to each other doing various things. But what most people don't realize is that 90% of this is a feature extractor. That's the hard problem that deep learning solves. It figures out how to automatically simplify your data down into a useful set of features that you can use for whatever problem you want to solve. It's only this last layer that's the classifier or whatever else you're trying to do. So we wanted to use this machinery as a feature extractor because we knew it would do a lot better than the simple things we tried before. So we did this. This is work led by Mike Walmsley, who's now a Dunlap Fellow in Canada. And he took a pre-trained neural network that was trained on galaxy zoo data, so images of optical galaxies. And you don't have to know too much, just notice that the blue line is much higher than the green line. So that was my original work, and this is with the new sets of features. So they do extremely well at identifying interesting sources and putting them close together. Something I'm going to come back to, though, is if you look at this plot, this is called a UMAP, where every single point in the plot is actually representative of an entire image of a galaxy. So it's a simplification down to just 2 dimensions, such that 2 points close together on this plot should look similar when you go back and look at the original images. The interesting sources are not anomalous. They don't appear as outliers in this space. They're buried somewhere deep inside. They're close together, but they're hard to find. They're hard to actually detect. You can't use traditional anomaly detection algorithms to find them. And Mike came up with a different approach that I'm going to come back to at the end. Nonetheless, these features are very good. And my PhD student, Willem Etzebet, who's here, and also has a poster that you should look at. So he did ran astronomically with that feature extractor in decals data, so looking at nearly 4 million galaxies, and managed to find these interesting weirdos here that, you know, some of my colleagues have different ideas as to what they all are. So it clearly works, and the whole algorithm clearly can scale very well. Just as an aside, Roland's looking for a postdoc, so I'll just advertise that there, just to embarrass him. All right, so the problem with using a pre-trained neural network is that if you want to apply it to data, it has to be quite similar to the data that it was originally trained on. Now, we wanted to run this for galaxies from Meerkat data, where we don't have nice big samples of human labeled data to train something on. So we had to do something different. And this is where self-supervised learning comes in. So self-supervised learning is just all the rage in machine learning at the moment, for good reason. So these are tools, techniques that don't actually require labeled data, but they can directly learn representations. And so this is an example of bootstrap your own latent, which is the algorithm we used. It sounds like magic. It sounds like it shouldn't work. But really, the idea is that if you take an image of a galaxy and you rotate it, you should still get out pretty much the same numbers for the representation for both sets of images. And so that's the way that these algorithms work. You have these two networks working together with different augmented views of your images, and it tries to learn a low-dimensional representation for you. So one of my other PhD students, Kuketsu Mahale, did some very, very nice work applying this to Galaxy Zoo data, where we could run the whole thing end-to-end without using any labels. So you can extract your features automatically, do clustering, and it will automatically put together, I mean, it's not perfect, but it does a pretty good job of putting together galaxies of similar morphology into the same cluster. And so basically what this means is it's kind of a shortcut to getting out your actual science, that you don't necessarily need these massive samples of labeled data to get somewhere. And he also managed to apply it to some radio data, which was very exciting. Okay, ironically, I don't have a lot of time to talk about time series data, but I just wanted to flash up a couple of slides just to point out that we work on this as well. So if this is an interest to you, obviously come and chat to me about these applications. But some of the early work was led by Sarah Webb, who's I think still a postdoc at Swinburne, where she had a large sample of optical light curves, and we did some unsupervised learning. We were able to automatically cluster them, run some anomaly detection, and discover some, a couple of variable stars, flare stars, things that people hadn't seen in that field before. We're doing the same sort of thing with Meerkat data. This is work led by Alex Anderson, who's now a Breakthrough Listen Fellow at Oxford. And it was really cool. He had a citizen science project, so we did have some labeled radio light curves, and we found that we could use astronomy to much more effectively detect these transients in the first place compared to the kind of more traditional techniques. We're also interested in spectrograms, so we were hoping to find maybe some unusual pulsars, FRBs, maybe the next latest, greatest thing. Mostly what you find is RFI, radio frequency interference. But in any case, we are interested in working in very high time resolution and frequency resolution radio data. And this is work led by my MSc student Jade, who's just finished, and also my postdoc Hanwoo Koo, who's also here. And of course, if you want to do transient or time series anomaly detection, you better not take too long. Otherwise, you might find something interesting, and by the time you want to look at it with other telescopes, it's gone. And so this is why real-time anomaly detection is very important. And this is work I've done for many years with Dan Mutakrishna, who's now a postdoc at MIT, and is also being picked up by my postdoc, Bertie, who's also here. And the idea is just how much data do we really need before we can reliably identify something as being interesting enough to trigger follow-up with other telescopes. And then finally, this is work I've done with Dan, but led by an incredible high school student, Rithwik Gupta from California, where we took the same kind of ideas that we'd shown for the image data, but applied it to time series. So this is using a pre-trained recurrent neural network as a feature extractor and then applying anomaly detection algorithms to it. It's simulated data, but it's already looking pretty promising, at least for certain classes of known rare sources. Okay, I want to finish off talking about Meerkat because obviously. So we have been for a little while applying astronomy to data from the Meerkat Galaxy Cluster Legacy Survey. This is a very beautiful, very rich data set. I extracted some sources. I've got a kind of different approach to doing a source extraction, finding some extended sources. And what you're looking at is the front end of astronomy as I'm just going through a random sample of sources. So they are extended. If you're not used to staring at radio galaxies, a lot of them kind of look like this, just blobby, boring things, nothing terribly exciting. I used the same approach that Koketo used for the optical galaxies, but now on radio galaxies. So we can use self-supervised learning to extract the features, and then this novel approach, which I'll talk about in a second, to actually find the interesting sources. And if I sort the data from, kind of most interesting to least interesting according to the algorithm, you can see it does a much better job at picking out things that aren't just boring blobs. And so here's a snapshot of some of the more interesting sources that we found. There are so many. Meerkat is so sensitive and at such high resolution. There are just so many interesting sources in this data set. I mentioned that we had to come up with a different approach, and this is really even a philosophically different approach from anomaly detection. It's not anomaly detection, it's interestingness detection. So this is work I'm doing with Larry Rudnick, who's an expert in radio galaxies. And we both went scoring different radio galaxies according to our own metrics in our head about what's interesting. And they correlated pretty well, which was exciting. But what it means is that we can train this algorithm, which we named Protégé, which does a direct regression on interestingness in an interactive loop with the user, which is me. And what I can do is I can train this algorithm to find the areas of this feature space that are most likely to contain interesting sources. And what's cool is it even found some stuff that we'd initially missed. We'd initially thought, this is boring. But then the algorithm says, no, I've got a good score for it. And you look at it again and you're like, oh, it is actually quite interesting. So my final slides is on something that kind of interrupted this work a couple of years ago, because while I was looking through some of the weird sources that I'd found with an initial or earlier version of astronomy, I found this guy. And I sent a message to Larry and I said, hey, Larry, what's this? And he said, I have no idea, let's write a paper on it. And we called it Sauron, which stands for wait for it, steep and uneven ring of non-thermal radiation. We think it's an orc, possibly an orc, an odd radio circle. It looks pretty different, but a lot of the physical properties are similar, so it might be the same sorts of things, like maybe a binary supermassive black hole merger causing this explosion, or there's some other models that we're kind of investigating. We did have a successful proposal on Meerkat, so we're kind of playing around with it and trying to figure out what this thing could be. But really, the point is that this was a source that was a little bit overlooked by the many scientists, myself included, who were looking at the MGCLS data. It's kind of small, it's a bit fuzzy, it's a bit hard to see, it's on the edge of the field. But when you look at it with machine learning, it pops up as being very weird. So it's an example of how machine learning can help us make discoveries, not just in large data sets, but also in very rich data sets, and find things that might have otherwise been overlooked. Oh, and just as a flash, there's tons of interesting sources in there. So these are just a couple of my favorite examples. So this is work that will come out in the next couple of months. Okay, so now what? So you found some interesting sources, some weirdos, some maybe anomalies. What does it mean? Where is the science? And I think that's really important. You don't just want to chase after the technical side, you want to do some science. Rare classes could end up being probes of the universe, like strong lenses or pulsars. If we find some anomalies, for instance, maybe find some things like more giant radio galaxies than we're actually expecting, it can make us rethink some of our models, some of our galaxy evolution models. Often rare sources like Sauron could be indicators of extreme physics, so they can be probes of extreme environments. But one of the challenges is that if you find something strange and you want to get more data on it, you have to convince the time allocation committee that it's worth going on this fishing expedition. So I think there's a lot of, a lot of us are super excited about anomaly detection in general, but we do need to get to science, and that's a much harder step. So thinking about how do we build motivation for following up these sources and getting some science out. Okay, I want to finish in the last 30 seconds just with a couple of adverts. The first is the Supernova Foundation. So this is a mentoring program for women and gender minorities in physics, which I run. We are always looking for more mentors and mentees. Some might look familiar. There's a few of our mentors in the room. So please spread the word widely. And then I'm running out of time. I think I've got a minute. So I should just conclude by saying machine learning is critical in facing the data deluge. I get the feeling the kind of people who come to this particular focus meeting are probably convinced of that, but in case you aren't, maybe I've convinced you a little bit more. But I think we need some form of automated anomaly detection or interestingness detection. And the machine learning is important, but the human in the loop is really the critical step. Our attempt at this is Astronomaly, and there's the link to the Supernova Foundation. I will finish with one more advert. If you came to Cape Town and you fell in love, there are postdocs available. These are Soreo-funded fellowships. So you have to write a proposal and you've got to jointly write it with your advisor. So if you're interested in these or you know someone interested, please just drop me an email. These are all photos I've taken, by the way. So this is no AI involved. And I want to end with this slide and encourage you to just take a photo of it. So this is my group, the Computational Astrophysics and Machine Intelligence Lab, a name we just totally made up. And they're all here. My two postdocs and two of my students are all working on different aspects of anomaly detection. Tandy's working on Bayesian statistics for fitting H1 lines. So if that sounds interesting, please check out their posters. You can find them all online or they're at the sessions during the week. And I will finish just by saying there's my email. I always encourage new collaborations. I would love to hear from you. And thank you very much for listening.
Thanks, Michelle. Questions?
Hi, Michelle. Nice talk. So I was wondering, for the transient anomaly, is there we checked whether the detection depends on the duration of the transient, whether the short duration, long duration transient, it has an effect on that.
Yeah.
And if I may ask a second question, have you thought about this interpretable machine learning, whether that has an application in your program?
Yeah, thanks, Sob. So the duration of the transient, that's exactly the sort of thing that Bertie is working on. So yes, it's definitely going to depend on the duration and in the kind of window that you look. And that's also going to depend on the cadence of the survey. So Rubin reobserves on average every 3 days. So if your transient is just 1 day and then gone, it's going to be very hard to find it, or if you find it, it's going to be very hard to do anything with it. And then, yeah, I mean, if your telescope's not probing on those scales, then you obviously won't be able to spot them. You might, like the thing is, especially amongst 10 million alerts, you might see a blip, but is that noise? Was that a satellite? Or, who knows what it was? So it's very difficult when it's on much shorter timescales than your cadence. But equally, if it's on very long timescales, you could have something that's weird over a period of months, and you've got to look on that timescale. So we have, in some past papers, looked at dealing with looking at different timescales, which is definitely problematic. And then certainly on the short radio side, we're looking on the scale of seconds. Those would be things for seconds or milliseconds, things like weird pulsars and FRBs. Again, there's a selection effect there. If you're not cutting your data onto the timescale that might be interesting, then you're going to struggle. And this is also where the feature extraction is important, that you want features that are sensitive over multiple timescales. So there's a lot to think about there. And I would say, in general, anomaly detection is going to be sensitive to duration and the timescales that you're looking on. And then what was your second question? Oh, interpretable AI. I think in the field of finding weird sources, the interpretable AI is to some degree less important, because this is not necessarily like a component of a high precision cosmology pipeline. For instance, we just want to find weirdos. But at the same time, this is something that we have started to explore, Larry and I, in terms of trying to understand a little bit like what is it that drives Astronomaly Protege, the particular algorithm that we're working on. Like, for instance, when it gets confused, why is it getting confused? And then we often find, oh, that's due to pre-processing. So there are techniques that we're using, like similarity searches, to help us understand what is the algorithm actually seeing and what do we need to do to our data to help kind of improve it, to find more of the interesting things, or more things that we're actually interested in. So I think it is a problem where it's less critical than compared to other problems in machine learning, but it is still useful to understand what the algorithm sees to try and improve it.
One quick question.
Thanks for the talk, very interesting. So you've clearly thought about the follow-up problem, so I was just interested, if you can take a minute, just speculate on, you already find rare things, and then like you said, you have to build a community around this is why this is the thing you want to follow up on, or I don't know, have you thought about how to narrow it down to like, this is the thing which is going to be pressing and what?
Okay, I didn't quite catch the whole question.
Sorry.
No, it's not your fault, it's the microphone's fault. But I get to talk about how do we actually, almost from a sociological point of view, how do we actually do the, build the follow-up around?
It's like, that, and I think, suppose you find, like you said, you're going to do the whole sky every 4 nights, and you narrow it down to I'm just going to yell, to a very small percentage of things, and then you have to find an even smaller percentage of things to do like the detailed follow-up on, like this rare radio galaxy you saw. Have you thought about that next step? Just speculate for us.
Yeah, I think it's really important. Actually, Guillermo and I have chatted a little bit about this. I think we already are moving to the era of where we have a lot of anomalies. We have a lot of rare sources. So there is an element of kind of picking and choosing the most exciting ones, like the things that, physically, looking at this, we just don't understand it. So there's some sources that are weird, but then you look at it and you think, okay, I can sort of figure out what's probably happening in this cluster to make this radio galaxy look like that. So that's a bit less exciting than the we have no idea sources. So those are obviously the ones that you tend to target. But also, I think when you find something weird, probably the first thing you want to do is see if you can find other examples of it. And if you can start building up a new class of sources, that is much stronger motivation for a time allocation committee. You can say, look, this is clearly real. We've found more than one of them. And so, you can start learning a little bit about the environments and things like that, and you can start developing your models. But I do think there is a fair burden of effort on the discoverer to try to actually, come up with some hypotheses, things that you can test, and it's quite a lot of work doing the actual science. So yeah, you pick and choose. You find the best, most interesting, rare ones, and also you start building classes, I think, to motivate it.
Yeah, thanks.
I should probably sit down.
Let's thank the speaker again.
Thanks.
So our next speaker is Fernando Ventura on enhancing discovery in large surveys with machine learning.
Good afternoon. So the problem that we're trying to solve is one I think we're all familiar with, and Michelle introduced it very well, which is that new instruments such as Meerkat and the upcoming SKA produce a lot of data. And we really need to find a good way to hunt through this data for, the things that we're interested in, either just classification or anomaly detection. So machine learning is obviously a very promising way to go about this, and we are interested in using machine learning in a semi-supervised or unsupervised way to automate the process of hunting down interesting sources as much as possible. And it's become more complex because not only do these new telescopes produce so much data, but the data that they produce is very crowded fields. We have a lot of overlapping sources, and when we have more detail on these sources, their classifications can become a bit more nebulous. It's not, 2 blobs is an FR2 and, 1 line. So we have more complex sources, and it becomes a much more difficult problem to classify these sources automatically as well as to find anomalous sources. So let me first introduce the approach that we've been working with. So first of all, convolutional neural nets, just briefly speaking, a convolutional neural network, specifically a deep convolutional neural net, you have multiple layers and a kernel that convolves over each layer, starting with the input layer and then every subsequent layer, and then you adjust this kernel based on your learning to produce some sort of result, and then we use these to produce what are called autoencoders. Now, an autoencoder really consists of 2 models that are stacked on top of each other, and the first one is our encoder model. So the encoder's job is to take the input image or data, whatever it may be, to produce some sort of code form in what we call the latent space, which is usually now a much condensed sort of much lower dimension representation of the input, and then the decoder model, which must take the encoded form and attempt to reproduce the original input. And this is something that you can train in an unsupervised or semi-supervised way, because if you stack the models together, then the input and the output are the same thing. So without having to target a specific label, you can train the models on a large number of images. And they have been they're well known in the broader machine learning context for anomaly detection, and these are specifically convolutional autoencoders, which means we built them with the convolutional neural net. So we also just stack these into ensembles, so we use multiple autoencoders together in 2 ways. We call them averaging and voting. So when we want to test a particular image against a trained autoencoder, we get a reconstruction score based on how well it could reconstruct, and if it's a pretty good reconstruction score on a particular source, we assume it's quite a typical source, so you really want anomalous sources to have a low reconstruction score. If you average all the scores together and test that against the threshold, we call it averaging, and if you test each one individually and then just take the most common result, we've called that voting. So we've been testing all this on the MGCLS, that's the Meerkat Galaxy Cluster Legacy Survey. So the first thing we do is we took PyBDSF to find our interesting sources. Then we took cutouts of only the extended sources. So for this, we were not interested in the point sources and blobs. Then we had a manually labeled set that we could use for our testing and training. And we augmented these sources by flipping and rotating them. And we tested, initially just a couple of different ensembles, including from a single autoencoder all the way through to a ensemble of 9 autoencoders. So just going over some of those results, the voting method worked way better than the averaging method. And what we did was we optimized it to give us more anomalous sources, more exotic sources, rather than giving us more precise results. That is to say, I'd rather look through 1,000 sources and recover 100 anomalies than look through, 200 sources, but I only get half of my anomalies back. I'd rather have more of my anomalies recovered than thrown away. But since then, we've been testing a new type of autoencoder. Oh, so just let me quickly show some of the types of sources that it picks out. And some of these are, of course, quite famous sources, but that's what you want. You want to know that it will find these types of sources in your data. Since then, we've been using a new type of autoencoder. So this is more of an off-the-shelf solution, but it's got a very good track record recently in sort of image generation and in the broader AI space. So vector quantized variational autoencoders modify typical autoencoders in A couple of ways. First of all, they are variational. So what that means is we want similar sources to have similar representations. So in latent space, there is like a regressional term in the training that says lump similar sources together in the encoded form. And the second thing it does is it builds up and then draws from a dictionary of discrete values in the latent space. That's the encoded form. The idea being that, you know, if you have similar items together, you could think of, say, similar types of features. For example, you might have, say, one name or word for that sort of thing in just how humans process things. So similarly, we would say, okay, break it down into a few discrete, well, not a few, but a number of discrete options rather than just having a continuous spectrum of latent representations. So this was created by Google DeepMind, and as I say, it's been having a lot of success. So we applied this to the same data, and these are some of the things that we saw. Now, first we tested the effect of the latent space size on those F2 scores, and I just want to make a note here. So the first number is it's a three-dimensional latent space, so we varied one of those dimensions, and then that's followed by the F2 score. And as you can see, a smaller latent space produces a better result. And the reason for this is, you know, you get worse reconstructions with a smaller latent space, but we really want to have our anomalous sources have bad reconstructions. Our goal is not to just produce the best reconstructions of all sources and all scenarios, but rather to force it to really make a divide between that which is typical and that which is atypical. And we see an improvement, first of all, on the previous generation of autocoder, the ones that we built ourselves, but we also see that as we push that latent space down, we get better results. So the results from the VQ-VAE, we see that we have a better receiver operating characteristic. That's just you know, for those unfamiliar, it gives us an idea of how well a binary classifier would perform with random would be along that straight line on the diagonal, and then above that, the area under the curve gives us a good measure of, you know, how well it's performing. Now, what we have here on the right is a histogram of the reconstructions, and you can see, oh, it's cut off the label a bit, but the orange ones are the anomalous sources that we labeled, and then the blue, we have the typical sources. Now you can see that there are a lot of anomalous sources that do get quite cut off from the mass of blue typical sources, but there's also still quite a lot of overlap, and solving that is really the key going forward to improving the performance. And we can speculate a little bit as to why some anomalous sources receive, you know, such similar scores to typical sources. So just to look at some of the, you know, some of the most anomalous sources and the reconstructions. So you can see the sources are at the top and the reconstructions are at the bottom. And you can see, for example, there on the left, it completely fails. And this is, of course, what we want, right? We want anomalous sources to be badly reconstructed so that we can pick them out as being anomalous. And you can see how poor the reconstructions are in general here. And this is, you know, a good show of what we want, you know, out of this algorithm. A poor reconstruction of the anomalous sources, helping us to identify them. But it does fail in a couple of sources, and we can speculate, you know, why that is, and it does seem to fail specifically when the anomalous sources don't have so much fine structure, and when typical sources have low signal to noise ratios, or they are quite small in their field. But improving this is the task going forward. Now, I just want to mention the work we're carrying on with at the moment. So first of all, the SPT survey is one that's very promising for us to apply these methods to, and we're hoping to do it so I borrowed these slides from Roger Dean. It's something we're hoping to apply this method to try and isolate interesting sources, and we're hoping to do this in a completely unsupervised way so that we don't have to sit and label sources. And other than that, we are hoping to make a larger catalog of extended Meerkat sources, as well as test new models going beyond just the VQ, VAE, and autoencoders to see where we can pick up some more performance, as well as a follow-up on any interesting sources that we do find out. Because of course, the point of finding anomalous sources is that we do want to follow up and study them, see what makes them interesting. That is, after all, the goal. So, thank you very much for your time.
Thanks, Fernando. Any questions?
Thanks so much, Fernando. Very quick question. What was the final size of your latent space that you ended up going with, that you found had the best performance?
I forget the other dimensions, but it only had a height of 2. So it was a 3-dimensional latent space, and the first two, that we kept it's a square and then height. So we kept that constant, and then we just varied the height, and we went with just a latent space of 4 in the end. So the height, that is to say, but the total dimensions I forget offhand.
It's really interesting. Thanks.
Hi, you said the reconstruction was poorer on anomalous sources of fine structure. Does that affect the classification as well?
Yeah, so that's how we make the classification, is the poor reconstruction tells us that it is anomalous. So that's really what we want. It's poor reconstruction on exotic sources. That's how we pick them up, I should say.
Can I ask a follow-up question? Yeah, and I thought machine learning algorithms tend to have a bias against fine structure. So is that just like an inherent property of neural networks?
So it really depends on the type of neural network that you're using. Some fine structure, it didn't really have a problem with. It's really when you start having these wisps of structure that go off in an unpredictable way, I guess. And interestingly enough, in some cases, it would introduce its own fine structure, just in some cases where maybe it thought it was used to a lot of sources with maybe, fuzzy sources, and it wasn't fuzzy enough for its liking. It would reconstruct them with too much, like imaginary detail, which also, of course, gives it a low score. So the score is how close it gets to the original. Yeah.
Let's thank the speaker again for a great talk. Our next speaker is Sambatra Andrianamina on emulating cosmological simulation dataset with generative models.
Hi. Hi, everyone. First, I just want to thank the organizer for the opportunity. You can call me Sam. I'm an operations scientist at the South African Radio Astronomy Observatory. So today I'm going to be talking about emulating cosmological simulation with generative model. So without further ado, I'll present my outline. I'll try to motivate why we are working on this project. I'll introduce the CAMEL project and specify the dataset that we use in our work. And I'll give one slide of the method that we used. Then I'll present the result and draw some conclusion. So why do we emulate hydrodynamic simulation? So hydro simulations are very expensive, such that any analysis that involves parameter space exploration is virtually impossible, because changing one parameter involves rerunning the entire simulation. The other thing that can be, the other way to use the generative model is to also, in the case of data augmentation, when you do ML-based, machine learning-based parameter inference. And the last case is in a case of simulation-based inference where your tool, your generated model can be used as a simulator. CAMEL's project is producing cosmological astrophysical data set to train machine learning. Its goal, amongst other ones, is to study the baryonic effect at a nonlinear regime, very small scales. It leverages two suits, Illustris TNG and SIMBA, and both produce thousands of 2D and 3D outputs. Each suite has its own prescription when it comes to stellar and AGN feedback. In our case, in our work, we use 2D maps that corresponds to 25 megaparsec of each region, and the resolution is 256 by 256 pixels at redshift 0. So in our data set, each instance comprises 3 channels. Now each channel corresponds to a field. In our case, we use hydrogen, gas, and magnetic field magnitude. And in other words, the output of our model is one image with 3 channels, mimicking an RGB like a normal picture. So each field has 15,000 maps, which are produced by varying the cosmological parameters and astrophysical parameters, which are the AGN feedbacks and the stellar feedbacks. Right, so due to time constraint, I'm just going to present a high-level overview of the method that we used, which is generative adversarial networks, or GAN. So the model consists of 2 competing networks trained adversarially in a zero-sum game whose loss function is shown here at the bottom. So the generator then takes the noise, a Gaussian noise generally, at its input and produce an image composed of 3 different channels. And then the discriminator is fed with either the training data or the fake data from the generator. And it attempts to classify, to see whether it's a fake one from the generator, or it's a real one in our case from the training data. So through the training then, the goal of the generator is to fool the discriminator. So at each weights update, it attempts to produce better image in order to fool the discriminator. So overall, that's the game in a method. Now the next question is, how does it perform? So on the left here, we showcase a sample of a real image on top, and then at the bottom, a fake image, right? So remember, as I said, each instance comprises 3 channels: the gas, neutral, hydrogen, and magnetic field. Right? So we can see here that the model is able to capture the typical features, like the filaments, the voids. And in terms of quality, it looks good, but it's not enough. So we need to make sure whether the data is consistent statistically with the training data. So how do we go about that? So we first generate 105,000 maps with a model, and we compute the power spectrum of each field in each instance, and we take the average. And in order to see whether the maps are consistent with one another, or if we want the channel, we compute the cross correlation between 82 fields in one instance, and we compute the cross power spectrum, and we take the average of the entire sample. So we do the same for the test data from the CAMEL data, and then represent the results here. At the bottom, we have the auto power spectrum, and the average at each K bin. The fake data is solid red, and then the fake one is the dashed blue. And the shadow area represents the standard deviation at each K bin. As you can see, they are in agreement, right? At the bottom, we show when the two power spectra diverge from each other at each K bin. And you can see at very small scales, they start to, you see the rise here. On the top panels, we show the cross power spectrum. Again, we see the consistency between the two power spectra. This actually tells us that in each instance in our fake images, the channels are consistent with one another, meaning that they all represent the same region on the sky. That is all good, but then what's next? So we need to have a bit of control over the generated images, right? So what we do then is to condition the image generation on two cosmological parameters, the omega matter and then sigma 8 as a first step. And I'll tell you why it's a first step in the next few slides. So again, we ran the test. We see the statistical consistency between the two data sets, the fake one and then the one from camels. They all agree with one another overall. And then I would like to draw our attention on the left figure. All of them have the same underlying set of cosmological parameters, omega matter and sigma 8. But on the left column here, we have instances of the real data set from camel, from the test set. And on the right-hand side, we have the fake images. And you can see that there are some variations in the field. Remember, it's the same. Each field has the same underlying cosmological parameters here, and you can see the variation. That actually tells us that indeed the GAN model does not suffer what they call mode collapse. Because you can see that you can run it many times. It produces different images each time. This is all good, but then the next question is, even though we have statistical consistency between the two data sets, there's no guarantee that we know for sure that the map that the generator produces corresponds to the initial cosmological parameter that we put at the input, right? So how do we go about that? So in a previous project, we attempted to recover cosmological parameters from H1, M-gas and H1, and M-gas and H1 and B, meaning one channel input, two channel input, and three channel input. And those regressors, they've been pre-trained, so we don't train them on the fake data. They've already been trained. So here we use those pre-trained model to predict the fake data set, right? So you can see all the values presented in the table is R-squared, which tells us how strong the correlation between the prediction and the ground truth is. So you can see we can recover for only wedge 1, we already recover the omega matter to a certain degree of accuracy, and then it increases as we add more channels. So the values in brackets are from the test sets trained on camels and tested on camels. But for sigma 8, which is a little bit challenging, for H1, it's a failure. But then when you add more channels, you can see the increase. So overall, we're more or less able to recover the underlying cosmological parameters in our generated map. So as a conclusion then, we've shown that it is possible to mimic camel data. It is possible to have some form of control on the generated map. And this tool can already be used for data augmentation. In the case of machine learning training, as we know that we need to inject some noise in the training data in order for the model to generalize. And it can also be used for emulation, for simulation-based inference as an emulator. But the limitation is that the predictive power of our model is limited by the number of parameters under which it is conditioned. So as a next step, either we use a deeper architecture or we use different method like diffusion model. Actually, we've already started to work on diffusion model and condition the image generation using astrophysical parameters as well. Thank you.
Thanks, Samatra. Questions?
I'm curious, so you put in cosmological parameters and it generates an image, and the image it generates is non-unique. How do you invert, so to infer the cosmological parameter, you fit it to an image and you're somehow inverting that?
No. So in another project, right, we were working on some regression tasks. We try to infer parameter at the field level, meaning that we have a network that we train to predict the cosmological parameters of an image it is presented with, right? So that is one separate project. So we use those models, those deep regressors, to actually predict the parameters that we injected in the model, in the generator model in the first place. So we just want to make sure that there's a correspondence, like we can recover the parameters that we start off with. That was the whole point of the test. Because in the end, even if you know for a fact that, okay, statistically speaking, you can mimic the camel data, there's no guarantee that if you use that for simulation-based inference, there's no guarantee that you're actually producing what you think you are producing, meaning the mapping between the cosmological parameters and the map that it generates. So that was the whole point of the test.
Any more questions?
Thanks for an interesting talk. I'm just wondering, can you elaborate a little bit on how you condition specifically on these two parameters?
Okay. This is not very descriptive schematic, but sorry. So what we did was, it's more of a standard approach. So first we have the noise, which is a vector length of, in our case, we chose 256 in the unconditional case. But for the conditional case, we maintain the length of that vector of the noise, and then we concatenate the two cosmological parameters with the noise, right? That's at the level of generator. So that's the part of the generator. We have, instead of having 256 in the conditional case, we have 254 plus 2, right? As for the discriminator, what we did was we again used the two cosmological parameters, which we pass through a fully connected layer, which we then interpolate to arrive at the resolution of 256, basically. Right.
That's super interesting. Thanks.
But there are different ways to approach the conditioning of a GAN model, but we chose the standard one.
Let's thank the speaker.
Okay.
Next presenter is Dr. Connor Bottrell on big mock data understanding galaxies with simulation-based inference.
Testing one. Okay, that's good. I didn't know I'd be following up a camel's talk. It seems sort of senseless to talk about big mock data now. All right. So first of all, thank you very much to the organizers for giving me the opportunity to speak at this very exceptional conference here in Cape Town. So this talk is titled Big Mock Data. And if you haven't gotten it from some of the other talks in this session, you might ask, well, we've got this data deluge from all these major observational surveys that are coming online or are currently online. So why do we need to generate more data when it isn't even real? So the answer to that, and the reason for that, is that the mock generally gives you some control over something for which you do not have control over observationally. You don't have a priori knowledge. It's something, for example, that you might want to, or you can only infer a posteriori. Sorry, this is the slide deck. So some examples of those things might be, you might want to know, for example, the assembly history of a galaxy like the Milky Way, or any other galaxy for that matter. And so to do that, you might want to connect the observable properties of galaxies, the things you can actually see, to those assembly histories, or the physical properties that diversify galaxy properties, right? The physical processes. And in addition, we don't have access necessarily to dark matter structures around galaxies, but we know that galaxies and their dark matter halos evolve and form concurrently, or assemble concurrently. And so because they assemble concurrently, the visible properties of galaxies, the observable properties of galaxies, should tell us something about the dark matter properties. And so this is very difficult to do observationally, but in a hydrodynamical simulation such as this one, the TNG50 simulation, where we model the evolution of baryons and dark matter through cosmic time, we can literally rewind the clock on any individual galaxy and assemble it and reconstruct its entire assembly history, not only of the baryons, but of the dark matter as well. And so we have access to all of this information simultaneously with a hydrodynamical simulation such as this. And so this is for an individual galaxy, but these simulations generate many thousands of galaxies like this. All right? But the problem with that, with the simulations, is they don't live in the observational domain. So what we need to be able to do first is create a forward model which brings simulations into the observational domain. And one example of this process, and we've heard of a couple here today, is radiative transfer post-processing. And so in radiative transfer post-processing, we assign SEDs to every star in the simulation based on its mass, age, and metallicity from a library of stellar spectral energy distributions. And then we propagate the light from those SEDs through the gas and dust in the simulation to reproduce what the galaxy would have looked like as if it had been observed with a particular instrument. In this case, we're looking at hypersub prime cam superstrategic program image of a face-on galaxy, so somewhat resembling the Milky Way. And so we can do this for just any line of sight. So we have an enormous amount of control over how we generate the mocks and the characteristics of the mocks. And furthermore, we can take these images and we can inject them into real survey fields such that they have the exact same systematics that affect the measurements of real galaxies. Because if we want to do any inference of between galaxy properties and their assembly histories or dark matter halo properties, it is fundamentally necessary that the things that we're giving as input to any simulation-based inference model are observationally tractable. All right, so we've generated about a million such galaxies. These are some examples from the TNG50 simulation, but we've also generated these for TNG 100, Eagle, and Simba, all using the same radiative transfer post-processing model. So these are the idealized images, but we've also inserted all of them into HSC SSP fields, and we also have the idealized images for LSST bands and a myriad of other bands for specific redshifts. So we have a million such mocks, and for each of these galaxies, we have full access to their assembly histories and their dark matter halo properties. So very nice test bed for simulation-based inference. Okay, and this isn't the only. I want to just quickly mention that this isn't the only sort of mocking process that is out there available. We heard about a couple today, including the anime mocking software. But we really have covered the full electromagnetic spectrum and the full set of data products that are produced by today's instruments, including integral field spectroscopy, such as the SimSpin and RealSim IFS software, and interferometry, radio interferometry, such as Martini. Okay, so the first question that we need to be able to tackle is whether the simulations actually produced realistic galaxy properties. Because if the observables that are being produced for the simulations don't resemble those that we see of real galaxies in the real universe, then any simulation-based inference is moot because those inputs do not exist for that can be applied, that exist in the real universe. So what we seek is we seek to first establish whether the simulations and observations are similar. And we seek to do this efficiently and fully, encapsulating all of the information that is encapsulated in the images, not just simple scaling relations such as size, mass, et cetera, et cetera. So we do this using contrastive learning. And so Michelle already laid out this very nicely. It was a very nice layup for this talk, actually. Because it's a self-supervised learning algorithm, which you don't need to apply any labeling. And I won't get into the details, but what the model essentially learns to do is it learns to extract a pertinent set of features which allow you to distinguish one galaxy from another. And it encapsulates these features as what is called a representation layer. And you can think of this as a bit of a digital fingerprint that encodes all of the features that are pertinent for distinguishing one galaxy from another. All right? And so using this as a basis is very powerful because you're using now all of the features that are extracted from the images rather than just a few. And so you can do the comparison really all at once. And so they're using this contrastive learning and feature and representation learning approach. And what we find, and I won't get into the details, but based on several metrics, we find that roughly 70% of galaxies in the TNG simulation, the simulation that we use for simulation-based inference, are in domain with respect to observations. And so this is actually a fairly conservative cut for what we decide is in domain. But what I wanted to say is that this is really a necessary basis for simulation-based inference. Because as I said, unless you're producing observables that exist in the real universe, you can't create a simulation-based inference model to connect observables to assembly histories or dark matter halo properties. And this is where we apply it to dark matter halo properties. So what we've got is we've got a stellar mass relation, which has a knee around M star, around the mass of the Milky Way, and we've got a halo mass relation here, or halo mass function here. And what we find is that at high halo masses, really there's only one galaxy, so at high halo masses, only the biggest galaxies can live in those dark matter halos. And so really the scatter in the stellar mass to halo mass relation, the ratio of stellar mass to halo mass in a particular halo, is very small at high halo masses. But as you extend to lower and lower halo masses, what you find is that scatter, the range, the diversity of possible galaxies that can live in halos of that mass, at fixed mass, is quite large, including their stellar masses and morphologies. And so what we seek to be able to explain is, if galaxies in their dark matter halos evolve concurrently, then the morphological properties of the galaxies that reside in those dark matter halos should give us some information about the ratio of the stellar mass to halo mass in those halos. All right, and so we trained a simulation-based inference model to do this. It was based on a normalizing flow. It was a normalizing flow model, and we used it to estimate both stellar mass and halo mass simultaneously, just based on the information that we extracted from the images, the morphological information about the galaxies. On the y-axis here, you're seeing the stellar mass, and the y-axis here is halo mass, and these are the true stellar mass and true halo masses on the x-axis. And what we find is that just based on this morphological and photometric information, we're able to very accurately predict both stellar mass and halo mass simultaneously. So that is to say that we're not just refining the scatter in the stellar mass to halo mass relation, but we're also predicting both of those features and the ratio simultaneously. And in particular, we find that 40% of the scatter in the stellar mass to halo mass relation, that's the intrinsic stellar mass to halo mass relation scatter, is described by the galaxy morphologies. So that is to say that 40% of that scatter is just completely explained by morphology. And so this is what we plan to do now, is we plan to apply this to galaxies from the Hyperspectral Prime Cam survey, for which we have dynamical masses, thank you, based on spectroscopy and also weak lensing. All right, so another application of this model is actually just identifying features of galaxies which are faint. So identifying features of galaxies which are buried in noise. And so the mocks can be used to train what is known as a diffusion probabilistic model, whose objective is to predict or generate a sample, a noise-free sample from data like this, to reconstruct the signal that is deeply buried in the noise, such as this puppy dog image over here. And so what you really need in this context are images that are noise-free, for which you can add sequential layers of noise to allow you to do this diffusion process, this backward process of iteratively moving backwards to a noise-free sample. And so that prior, in this context, is the idealized MOCs that have no noise, that are just the pure radiative transfer post-processing output. And so we applied this, one of these diffusion models to galaxies from the HST, at roughly intermediate redshifts. So this is that galaxy here. This is the ground truth that we give to the model that has been trained on priors from the MOC galaxies. And so here we have samples that are generated by the model. So these are 2 samples, and then we have a median generated over 300 samples from the model. And what we see is it's predicted some features that we can't really get access to in the HST image, but which are visible in the JWST imaging. So this is the JWST ground truth of the same galaxy, but that the model did not see during training. So you're able to reconstruct features which are deeply buried in noise that are really there in observations. Now, this can't necessarily only be applied to HST images. You can also apply it to JWST, for which the data is noisy there as well. So you can just keep going deeper and deeper like an onion. All right, so the last thing I'd like to mention is that these models can actually be applied out of domain to some extent. So long as the context is still maybe astronomy or something, they can still be applied out of domain. So here we have 2 galaxies taken from the D-sharp ALMA continuum survey of protoplanetary, protoplanetary disks. These are protoplanetary disks taken from the D-sharp ALMA images from ALMA continuum. Starting with visibilities, you turn them into these actual image plane maps using 2 deconvolution algorithms which are standard in the field. So then you can also train a diffusion model which is based on galaxy data. So we took galaxies as the prior in this case. We then starting with the visibilities, turned it into these. So now we're able to reconstruct protoplanetary disk data from a galaxy prior. So the model even works to a reasonable extent out of domain, which is quite fascinating. So I think I'll end there. I just wanted to iterate that I think that MOCs generated from large galaxy simulations are very useful for interpreting galaxy structures and relations. You can use contrastive learning to very sensitively evaluate the accuracy of a galaxy formation model at the data level, so at the level of the images, rather than just simplifying scaling relations. And lastly, that these MOCs can be used to link observables to things like dark matter and galaxy assembly histories, some other work in progress, and also reveal the hidden structure buried in noisy data. Thanks.
Thank you. Time for a quick question or two.
Hi, thanks for the talk. Just out of curiosity, because I don't know how important it is that your mock data are close to the realistic ones. Have you thought about to assess the out of distribution sample? Have you thought about using some density estimator to see whether trained on the real data, and then you get some form of score on your mock data, and from the distribution of the 2 scores, you can really see whether your mock data is out of distribution. If that makes sense.
I don't think we've explored that specific model as a metric for evaluating whether the simulations, that the mock data is in domain with respect to the observations.
Right.
But I'd be happy to talk about this after the session. Yeah.
Sure.
Okay. All right. Sorry here. Thanks so much, Connor. That was really interesting. I was very surprised, as I'm sure you were, by the last point about being able to reconstruct the protoplanetary disk. My guess is that's got more to censored. That's got more to do with the noise properties in your simulations than necessarily the sources themselves. So, first of all, because if it's learning more about the noise in order to effectively deconvolve it away.
Yeah.
So do you think that's true, that the noise properties in your simulations are close enough to what we really see in ALMA, which in a sense I find surprising, or do you think something else is going on?
I'm not terribly sure, actually. It seems, so we do know that we're trying to very accurately model the noise properties, but unless you have a prior for which the data is reasonable, you can't train on puppy dog data and expect to reproduce galaxy features. But seemingly, when you're as close as this, it just works.
It's very interesting.
Yeah, thanks. I'll keep it quick. I have many questions that we can maybe talk about afterwards, but can you comment on the computational complexity of your technique compared to, for example, clean or other deconvolution?
It's much more computationally expensive. So generating an individual sample from one of these mocks takes maybe 30 minutes on a GPU. So generating an individual sample here, and there are 300 that went into this mock, takes about 30 minutes on a GPU. So it's much more computationally expensive, certainly, than these deconvolution algorithms, for which admittedly I don't know how long it takes.
One last question.
Thank you. This is Clécio Debon from Brazil. You have a limitation on your magnitude sample, and because things are getting, as far as understood, you got up to Z 0.1 in your simulation-based inference, right? And there are fairly close galaxy and likely to be big in your stamps. So do you have any limitation in your magnitude in your sample where things get messy and fuzzy?
Yeah, absolutely. So we haven't quite tested this yet, but we absolutely do expect that as the distance and signal to noise degrades the quality of the data products, the morphological measurements, et cetera, then the inference will get poorer, right? And so what we plan to do actually is have individual models trained at different redshift intervals, because training a model that is attempting to do all of this stuff simultaneously over a large swath of redshifts will be very difficult, I believe. It'll be very difficult for the model to figure out, really what it's looking at. Whereas if you have models which are trained on, each sort of in redshift buckets, then it's a bit more of a tractable problem. But yeah, absolutely, we expect signal to noise and measurement quality to affect the model's capacity to make good estimates.
Let's thank the speaker once more. So our last presentation is virtual. It's by Gordian Edenhofer on the statistical and computational challenges in astrophysical imaging.
Yeah, thank you. Thank you for having me. I see that we're running a bit short on time, so I would try to skip some of the content. And if I wasn't able to talk about or answer the question that you wanted to ask, you can also reach out to me by mail after the talk. Right, so my name is Gordian Edenhofer. I'm a final year graduate student at the Max Planck Institute for Astrophysics and the University of Munich. And in this talk, I would like to discuss the statistical and computational challenges in astrophysical imaging. So I would not only like to focus on the problems in astrophysical imaging, but also talk about how we tackle those in our group and what kind of methods we came up with to address those. Right. So what are the challenges in astrophysics, in my opinion? So first, in astrophysical imaging. First, let's define what I mean with imaging, because I will use the word in a very broad general context. Let's imagine you have some purely statistical problem where you have some scattered points in a 2D plane, as here shown on the left, and you want to, from those points that in themselves don't tell you a lot, you want to infer the slope. Let's say the slope has a physical meaning to it, like you can interpret it as some quantity that you're interested in, but in the data itself, you can't really see that slope itself, right? You need to do a statistical inference to go from this noisy, incomplete data on the left to the slope, to the human accessible physical quantity of interest to the right. I would call that imaging as well, because this is actually exactly the same problem that we're trying to tackle if we have huge radio astronomy data sets and want to get out an image of M87 star, as, for example, here shown on the right. The problem is really the same in the sense that you have noisy, incomplete data, and you would like to map it into a human accessible space. On the right, that means pixels, where you now know the brightness of those pixels. On the left, it's just a slope parameter. And statisticians tend to think about problems that are more similar to the thing on the left, where the parameter space is not huge, well, a couple of dimensions. In this case, that's only one in this example. And the data is also of manageable size. But in astrophysics, we kind of have a very different problem. We would still like to quantify uncertainty. We would still like to do the same thing of mapping noise incomplete data rigorously to a posterior distribution of the quantity that we're interested in. But we do have in the example on the right, we have millions of parameters that we need to infer to do those. And those poses computational challenges and statistical challenges. Computational challenges simply because, well, we're facing a lot of data. We have to work with all of those parameters, all of this data and all of those parameters. And statistical challenges because we still have noisy data and incomplete missing slices of the data. And we want to propagate those uncertainties that we have in the data also to the quantity that we get out, to the image that we get out. And those two challenges are kind of not really unique, but they are especially pronounced in astrophysical imaging, where we do tend to have a lot of data and some more complicated physics and models with a lot of parameters. Right, and in our group, we were tackling exactly those kind of problems. We were, a part of the group is looking at M87 star, trying to image it more accurately, this is work led by Felivaris et al., where he created a physical model of how M87 star should look like. This model has many parameters, and then went from this, how it is supposed to look like from the physics to the data, developing like a physical model of how the image should propagate to the data, and encountered there and a lot of parameters and a lot of uncertainty that thoroughly needs to be propagated. Other people in the group are focusing on radio astronomy, where the problem is exactly the same. You have like millions or even tens or even hundreds of millions of parameters because you're mapping an image where you don't know the value of every pixel, and the most general thing to do is just treating it as an independent parameter. And this is shown here in the center. This is work led by Jacob Roth, where he inferred those hundreds of millions of parameters in radio astronomy from radio interferometric data. And one problem that is very dear to my heart, that is here shown on the right. Maybe I can show, yes, maybe we can play the video. That is about our own Milky Way, where we try to learn the distribution of interstellar dust out to 1 kiloparsec from the sun. So basically map the shape of the galaxy in a tomographic problem and treat it as a tomographic inversion problem. And all of those kind of problems have in common that they have a lot of parameters, they have very noisy data, and we found that the statistical tooling that was currently out there was insufficient to kind of tackle what we're interested in. So what we ended up doing is we developed a new Bayesian modeling framework called NIFTY, short for Numerical Information Field Theory, where we try to develop statistical algorithms that are as fast as possible so that we can tackle those kind of problems at all. If we are able to solve the problem, if we are able to work with 1 billion parameters, we try to make it as accurate as possible, but the focus will always be on being as fast as possible. And then, if it's cheap, also focus on statistical accuracy. Right, so what is NIFTY all about? NIFTY proposes a switch of mindset that's not new to statistics, but often not used. So that's known, but not used in practice often. We propose that all models are written in a generative fashion. You heard a lot about that already during the preceding talks, where instead of thinking about how you go from the data to the thing you're interested in, so let's say for the data of M87 star, the radio interferometric measurements to the image of M87 star, we propose that you rather think about how you go from the image that you would like to have, so the photon, the wavefront hitting Earth, to the data. So you start to think, so we propose that you think about how this wavefront hitting Earth propagates through the interferometric devices, modeling all the physics there, and how it goes through all the various measurements, processes, and noises added there, random stochastic noise, and then to the actual thing that you have on disk. By encoding that in a generative model, you allow for a very efficient kind of inference that exploits this generative structure to get to the quantity of interest, the image itself, in a very efficient way. There are a lot of things that we do underneath that we do underneath to make this as fast as possible. We also tap into GPUs if they're available to even speed up the inference if the model allows for that. And there are a lot of details that I unfortunately need to gloss over here. More precisely, since I just talked about it on a very abstract level, Nifty provides two things. It provides you a generic modeling toolbox focused on image spaces. It has, for example, structured Gaussian process models where you can define domains of how your problem is supposed to look like, saying that this is 128 by 128 pixels, because saying that those are pixels already helps the statistical inference a lot, because it imposes a certain structure. Then we have radio gridders and ML models that you can all duct tape into Nifty. And as a kind of second component, we have approximate posterior inference techniques, where we are able to sample or get posterior estimates of models that you build with the toolbox on the left. In contrast to existing models, we really focus on really high dimensional models and inference. So compared to classical Gaussian process models or statistical inference models, we think about problems where you have hundreds of millions of pixels or just generic parameters that you would like to learn. To give you a feel for what this actually looks like in practice, I would like to talk about the research that I carried out doing my PhD. I have the videos loading, yes. As part of my PhD, I reconstructed how our own galaxy looks like in 3D. So modeled the distribution of dust in all 3 dimensions out to 1 kiloparsecs, 1.25 kiloparsecs. Here I'm showing actually exactly this image. The sun is at the center, and the distribution of dust here is shown in 4:30. I'm going to play the video in just a second. So how I ended up modeling this in Nifty is that I started thinking about how dust should look like in 3D. So I applied a very generic model, just saying how I think voxels should be related to one another, and then taught the model in Nifty how you can do line of sight integrations from the sun to different locations, because this is how the data is measured. My data constraints come from extinction data. And just doing those 2 things, telling the model how dust should be distributed, and then from those dust distributions, how it can get to the data, how it can do those lines of sight integrals from you to locations in the map, from the sun to locations in the map, allowed Nifty to then do the inversion and give me this beautiful map. Or to be precise, not only this map, but like with uncertainties, so 12 different realizations actually of this map. And we're here looking at the posterior mean. And since this is a 3D result, I would like to briefly show you how this actually looks like. Here we're now zooming around, we're rotating around the sun and looking at very famous molecular clouds that are adjacent to the sun. We're seeing like a Radcliffe wave that is now right in the center, and Chameleon, Musca, Colsec, a lot of famous clouds right around the vicinity of the yellow dot, the sun. Right. With that, I would like to conclude. Thank you for your attention. And if you if you are interested in Nifty, feel free to check it out. The link is here. If you have any further questions that we're unable to answer now, please do reach out. My name should be pretty easy to Google. Yes, I'm happy to take any questions that you can throw my way now.
Thanks, Gordian. Any questions? I seem to have a question on Zoom. Can I just quickly read that out?
Yeah, please.
Oh, sorry. Can you?
Sorry. Yes, 1 second.
Sorry.
What insights or interpretations do you draw from findings that have been presented? So in the context of statistical models, I would say a generative picture on your problem has been a really fruitful representations of problems, because you're able to model the physics much more precisely, because you're really thinking about what the physical processes are that go from the quantity of interest to your data. And this allows you to more thoroughly also represent the noise statistics, the stuff that you don't want to model. So this has been really interesting, seeing that how impactful it is to pick this generative perspective. And then about the physical results, if you're taking statistics into account, if you're thinking about uncertainties, if you're thinking about data uncertainties and incompleteness, you tend to have much more accurate results. And this is what we see here all over, which we see in kind of all projects throughout, is that the 3D dust map, for example, has a much higher resolution. We're able to achieve a much higher resolution thanks to us thinking about statistics much more thoroughly, while still being able to tackle it at all. This high dimensional problems, and the same holds for Magnetism 7 star and the radio galaxy that I'm part of a radio galaxy that I'm showing here in the background.
Any more questions? Yeah. Last question.
Great, thank you for the talk. Just a naive question. So if I understand correctly, if I were to use Nifty in the case of likelihood-free inference, I no longer need to have some form of data compression, right? Because Nifty seems like it is able to take images as input.
Good question. So likelihood-free inference proposes that you don't analytically write down your likelihood. That's something that we're currently thinking about, but not fully support yet. So what we currently mostly worry about is noise statistics, where you do know how the noise is distributed and where you can write down the analytic form of your likelihood. Likelihood-free inference is a bit harder because what we need to approximate the posterior very accurately is a metric of your likelihood. And a lot of likelihood-free models probably don't provide you with that metric. Or if you're doing a neural network approach, actually that works. If you have a likelihood that it's just a neural network, that would actually again work. But if you have like a more generic concept where you can't compute certain things about your likelihood, then Nifty is probably not well suited for those.
Okay, thank you.
But basically, in short, you need to kind of, yeah, sorry.
No, go on.
I just want to say, yeah, you need to stay, especially about the likelihood, you need to stay in a certain analytically accessible regime to make the kind of statistical approximations that allow Nifty to be very accurate.
Thanks, Gordian. Thanks for giving the virtual talk. Let's thank all our speakers once more. So that's the end of it. Next session is at 3:30. Thank you.
1, 2.
Wait a few minutes and take it over.
Rob agrees.
I'll just remove the slides that mention you.
Oh, okay.
You were in your email, yeah. But we wanted to say,
Stuff going on. When it's very directional, and it needs a much better pop shield.
But you know, if people got off just to the side, you can't hear them at all. So it just needs to be quite directed. So we're just going to wait another minute or so to collect people from coffee. They just gave out free food downstairs. Oh. Couple more? Okay.
You can cut me short.
Everybody's here, wonderful. Well, welcome back excuse me, to the final session today for the Focus Meeting 7. We have 4 talks, 2 invited talks and 2 contributed talks, and primarily about systems and software for working with large data sets in astronomy. And our first presentation is from Professor Rob Simmons from the University of Cape Town and the Inter-University Institute for Data and Astronomy, talking about the LUFU cloud system. So I'll give you a 5-minute warning, Rob. Okay, right, thank you. So I'm very pleased that they decided to give out free food and coffee downstairs just before my talk. I very much appreciate that. And I also point out that that's my dog. And 2 years ago, just before I bought my dog, I was making fun of one of my colleagues who has 2 dogs, and he has pictures of dogs everywhere. And I said I couldn't understand why, if you own dogs, you have pictures of your dogs everywhere. 2 years later. So anyway, what we're going to talk about is our LUFU system that IDEA runs. So talk about the hardware architecture, the middleware, talk about our science gateway, which is the big thing we did last year. Talk about user base, the astronomy projects and the bioinformatics projects, and something about the path forward. So SAT established in 2016. In fact, it was first running in 2015, but that was only really in a test mode and really only used by our little group. And so now it has over 4,000 processor cores, over 12 petabytes of storage raw. We've got another 2 petabytes arriving in 3 weeks' time. And it has a 50 gigabit per second compute interconnect. So we're using the SN2700 switches, the Ethernet switches. So we didn't go for InfiniBand, particularly because in the early days, InfiniBand did not work at all well with the virtualization software. 100 gigabit per second storage network, and we have 100 gigabit per second link to SANRAN. So we have a pretty much direct link into the CHPC POP, which then goes directly into the path across to London. So we're utilizing OpenStack infrastructure as a service middleware. So OpenStack is now by far the most popular open source cloud software. It was developed by NASA, and then a company called Rackspace spun off and continued to develop it. We utilize Ceph for storage, and it provides all these different types of storage, and it's all very, very automated in the way we set up the different storage nodes. So we have a Horizon dashboard, which is part of OpenStack.
which allows you to go and set up how much storage is assigned to different volumes and different groups. And this means that we have a great way to create custom configurations for different projects. And so, me, I'm from the HPC space. I was CTO of Compute Canada for 10 years before coming here. And basically in those systems, it's very hard to configure things for specific projects. They're really set up as massive systems which are just used as one big iron piece of equipment. So utilizing these sort of services, we get the ability to just within a dashboard go and say how much storage is assigned to different groups and how it's assigned to different shared file systems, and that gets us around all sorts of security problems. We wanted to, this is moving on to the IDEA Science Gateway, which is what we did last year. And what we wanted to do is utilize best-in-class web applications with unified branding. These microphones are very dodgy. So if you're old enough to have lived through the grid days, there used to be lots of these toolkits for creating science gateways. And I'm very US-centric, I'm afraid. I lived in North America for 20 years. And so I was mainly tracking what was going on at places like SDSC and TerraGrid and Exceed. But they sort of slowly filtered down to a smaller set of these frameworks. Still, there were lots of them, and it was just a nightmare to maintain these things. And one of the problems is that you'd get funding to create one of these things, which would cost several $1 million. But then getting funding to maintain them was really hard, because that just isn't interesting to the funders. So best-of-class web applications linked to Sapphire Edge again, so that we could just let people use their institutional passwords. We didn't have to store their passwords. That saved us a lot of support overhead, because people forget their passwords. People forget their SSH keys. So we did all sorts of things to limit the amount of support overhead we did. And then we spent about a year with a couple of my guys, well, me and a guy, experimenting with different tools to achieve these goals. But we had lots and lots of problems. It was not fun. So a lot of the tools were very hard to install, didn't work as advertised, or just were incredibly unreliable. And so we couldn't trust them. But then just really fortunately, as we were moving up to where we had to make a drop-dead decision about what we were going to deploy, there were some big improvements in a few tools, and things that were not working suddenly were working. So that was very lucky. So this is my dodgy design. So just by the way, I was on the core architecture team for the SKA Science Data Processor, and this diagram would not have passed the muster. But anyway, one Monday morning, I created this very rough diagram. I don't know if I can point, but what it shows is a human that's talking to a gateway, and that's got some pages in it that we were going to create ourselves, very simple pages. But then we would link through, at the top, a single sign-on login system, which would then connect through to Sapphire and on to Edge again, but that could talk to all of the university IDPs. And then the other stream coming down towards me are the best-in-class services. And so that was, you wouldn't believe in the SK, we would have taken at least a year to produce a diagram that achieved less. Oops. So moving on, if this still works. So the gateway, looks like this when you went to go to the application dashboard out on your left-hand side.
You can't point with that device.
Can I? Oh, you can. All right. Too late now. So, okay. So if you click on that, then what would happen is that you actually get this interface that would give you different ways of authenticating with our system, and then that would pop on through to something provided by Sapphire, which would allow you to pick your university. In my case, I picked UCT, and then I got a UCT login, and then from there, I'd get into the system. This is the page you'd get if this was the very first time you'd logged in through Sapphire. You wouldn't get that afterwards. But the point here is that IDEA never sees this. This is just redirected to UCT. I authenticate with UCT. UCT tells Elifu whether I am who I say I am. So that means that Elifu is not handling any secrets, which means we are relieved of some security issues. So yeah, then you just get back to this page, and if you click then on the application dashboard, this is actually a screenshot that I made yesterday, and the initial dashboard actually had more things on it, but we sort of reduced it down, and we now have some things in menus which are used less. But this just gives you a way. You're now in a single sign-on environment, and this gives you access to all of these different tools. So we can click through to Jupyter and have access to all of these different, all of your different notebooks there. We can click through to Carter, which is a tool which IDEA leads the development of, and I wrote some of. I didn't mean that to happen, but it was quite ironic. But yeah, Carter has a big team of developers in IDEA, Asia A, NRAO, and the University of Alberta. And that's actually an image by Russ Taylor. I said I wouldn't mention him, but I have. And it's something about polarization, and if you want to ask me a question about what that's all about, don't. So then we can also go to a container registry. So we have containers that hold different software that have all the different tools that that people can use. So yeah, there's a big listing there, and you can add your own. And this also gives you the ability. So one of the things with Singularity is what you use is you need to have root access to actually build the container. You don't need root access to run the container. By using this registry, we can actually have a subsystem behind it that can build containers for people, so they don't need root access. So that's all sorts of things we do to try and make this easier. So then we just have a very simple file access, just something that people are used to, but not greatly interesting. And then we just have pages for SSH public key management. You know, as I mentioned, that users forget their passwords on their private keys. And so one of the things that we used to have support people quite often get is people saying, can you install a new public key for me? Well, now they don't have to do that because they can log into the system, not using our authentication system, using their institutional login system. And if they forget their password at their institutional site, that's their institutional site's problem. But generally, their institutional sites will have ways of them being able to self-manage resetting their passwords, which is just something we don't need to support because their institutions support it. Anyway, this is some usage. I won't say whose that is, but you might be able to guess. It's not mine. Yeah, and then this just shows you looking into the OpenStack dashboard, so users can. We actually ask people to ask permission to get access to OpenStack, just because there is a learning curve there. So, but this gives you the ability to go and set up your own networks. So using all tunnels and things, so it's all secure, and you have access to various different resources which you can allocate. You can create new virtual machines and networks. This is just showing a list of network shares. So these are all SFS shared file systems, which have been created and then can be linked to or mounted on to particular VMs using a secure code. So that's all encrypted as to how you connect to those shares. I don't think, yeah, this is quite a cut down presentation. So, but we can also make these block volumes, and they're generally accessed from SSDs. And so we can just create a volume, and you can mount it onto a machine, such as just as if it was a hard disk array. And so, yeah, we were working with the Meerlit guys the other day, and they wanted to add a lot of SSDs, and then we pointed out to them that they'd been using a lot of SSDs for the last 2 years, and they hadn't known it. But anyway, that's what these virtualized systems are like. So we're not really, we've never wanted to be an archive. We really wanted somebody else to be an archive, because an archive is a different activity than running a computing center. And it's also, to do it properly, you have to spend a lot of money, because you need to buy that big tape library to start with. And in my old job, I bought 6 of them, and they cost about $3 million each, and that's before you put a tape into them. But the point is, then you can fill them up with massive amounts of data, but there's a big initial cost. So, we do some of this, but we'd really like somebody else to be doing these. And there's a government organization, DRISA, who are trying to do some things with data management, and it would be really great if they could take this over. So the government people, at least, are interested in students. So this is the distribution of astronomy students. So, just peaked out with the PhD students, but followed by postdocs. And yeah, we have about 560 total active users. Figuring out what an active user is quite difficult, but because I'm sure we have probably about 1,500 actual users. It's just they don't actually necessarily use the system. So try and figure out what an active user is. And then astronomy users by country and institution. So we have South Africa here. Yeah, a bit of an anomaly. I didn't make this slide. Jeremy Smith, our operations director, made it. And I noticed we've got IDEA here, but we've got UCT, UWC, and UP, and they're all in IDEA. But this is just because of the way our accounting groups are set up, that it just happens to come out like this. But anyway, then we have a bunch of people from the UK and the US and various other people, various other places. So we support a bunch of Meerkat large survey projects. So far, 77 Meerkat open time projects and over 20 director discretionary time projects. And then we've got Meerkat large survey projects down there that we support. So bioinformatics, I've said very little about bioinformatics in this talk. In fact, I've said nothing about bioinformatics in this talk. So CBio at UCT was one of the original founders or original funders of ELIFU. And they work on our system. There's about 140 active bioinformatics users, and they have a whole bunch of projects. They're a very, very big African collaboration group. But one project we're working on is Eloise, and I mention that because I'm one of the PIs of it, so you may as well mention the things that you actually get credit for. And this is a platform for data processing of data sets for novel health discoveries. And one of the things that the IDEA staff have been working on is modifying this Gen 3 bioinformatics platform to work on OpenStack, because previously it's just worked on Google. Path forward. I would like an updated national/international authorization service. So we have used in the past, I didn't have it on these slides, but we have used in the past the EGI Connect system, but that's all run out of grease, and there's some just delay in getting people registered into it. So, and as well, it's using co-manage, which is an Internet 2 tool for doing group management, which is a very nice tool, but it's getting old. And so, nowadays we have Keycloak, which is a very nice tool, but it isn't designed for quite this purpose. But there are a number of groups working on trying to make it work for this purpose, because then you'll be able to use the same code base that lots of groups are using that are not doing the distributed stuff. So we're planning to deploy data replication systems. So we've been playing many through show like everyone else, and yeah, we're not quite there yet, but we've got some funding to send one of our people off to CERN to do some learning about that. And Carter, lots of things going on with that, and that's actually turned into my main research toy. And a big thing we're doing is improved collaboration features, which Russ has either talked about or he's going to talk about. But we have this concept of workspaces that you can save and then share, but we're changing the way they're going to be organized, and that's going to be nice. We're also experimenting with the microservices architecture. So currently we have a big monolithic backend for Carter that that has to run as the end user, because we're talking to POSIX, and POSIX only understands actual end users. But with the microservices one, we could have lots of the services being run just as system users and being shared by a whole group using a Carter cluster, and only have the actual file readers running as the end user. And that would also enable us to run multiple file readers to the end user and use multiple languages for the different microservices. We also need to improve deployment for HPC and Kubernetes systems. That's a real pain in the neck. If you look at the Jupyter documentation, you'll know it's not easy. And lots of science features. So, need to extend bioinformatics science gateway. That's not hard, we just need to devote time to it, and most of our support goes to astronomy just due to the way we're funded. And I didn't mention the IDEA pipeline, but we need to extend it to handle heterogeneous arrays, because Meerkat Plus, which is Meerkat with the additional dishes which are funded out of Germany, is a heterogeneous array, so that's tricky. So anyway, I have come to the end of my time that Russ gave me. And so anyway, we've been in production for some time, have very high uptime despite load shedding. We've only had one outage due to load shedding. We've had some outages due to other things, but only once we had an outage due to load shedding, and that's just because the generator got a coolant leak and stopped. IIS approach makes it easy to support a wide range of applications, much easier than on an HPC system. Easy configurable storage provides great flexibility to how we support projects. Gateways provided easy access to best-in-class applications, not things that we've just cobbled together to fit into some grid toolkit, which is then deprecated within 3 years, and appear to have many happy users. And that's my dog. It turns out I'm very bad at training dogs, but fortunately he's into online learning. And this is him watching a YouTube video about when to come. Russ?
Okay, quite an answer information. Oleg?
Thanks all. lovely dog and great talk, but above all, thanks for all your work on ILIFO. It's a great facility. I've got a question. Do you have plans, besides Carta, do you have plans to deploy Kubernetes support on ILIFO itself?
Yes, we're mainly focusing on it with Carta to learn about it. But we have, we went down a bit of a side track, which is unfortunate because we suddenly found out that all of these pseudo SRCs, the SK regional centers, a lot of them were adopting CANFAR, and we wanted to do some work on CANFAR because we were not quite happy with the way they deployed Carta into it. But then we just hit some problems with some dependencies which we didn't know about. So that diverted us a bit from our Kubernetes work. But we've kind of decided we're going to go back fully to our Kubernetes work. And as well, we were talking with Jeff Kern last week. And we're starting a collaboration on that in September.
Okay, excellent. I was going to bribe you with beers, but sounds like you're doing it anyway, so I'm glad to hear that.
Thank you. Any more questions? Yep.
I think I saw you displaying a page where users can select different, I don't know what your environments or other things to start up in this platform.
So I mean.
Yeah.
Oh, this one.
Yeah, the container registry.
Yeah. This is just it shows the containers, and you can either download the containers directly, but we also have them mounted in ILIFO directly. So as long as you know the container number, you can just mount them directly without actually having to download them.
Yeah, in fact, that was my question. So if I were to come into this platform and I wanted to do something specific, some particular type of data analysis, do you have a way for people to say, I don't know, search on like a description of what the container is, or how would I know what a good container is coming into this?
I wish I knew, but I mean, what I'd ask you to do is go and try, and if it doesn't work for you, tell us what we're getting wrong. But you can always, but then, you know, the really nice thing about containers is you can just build one on your laptop and upload it.
Thank you.
Okay, thank you again, Rob.
Okay.
So our next speaker is Oleg Smirnov. He's going to talk about some software.
All right. Right, so if you're wondering what happened to 1, 2, and 3, you should have come to the poster session. So I'm going to talk about workflows, data reduction workflows from a radio interferometry context. And if you do radio interferometry, you will recognize that we make beautiful images. And the way we make these beautiful images is by running pipelines that look a little bit like this, right? Does this look familiar? Good. And there's another aspect to this, is that our pipelines are largely siloed, right? And we've got a lot of siloing in platforms as well. Some people process their Meerkat data on their local fat node or a cluster, like I do. Some try CHPC. Actually, I don't know who does it on CHPC. ILIFO, of course, is a big player, and cloud, question mark. I'll get back to that later. But the siloing happens because we also have various pipelines, and these pipelines are not compatible with all the platforms we are running on. And another taboo word here is reproducibility. I don't hear it at radio astronomy meetings. I think in radio astronomy we don't have a reproducibility crisis because we never try to reproduce anything, because we know it's not going to work. So I've got a picture of silos with clouds here. I chose it deliberately because I'm going to pivot to cloud a little bit. Should we be using the cloud? Now, I am firmly on the fence on this issue. You can see a picture here of me sitting on the fence, staring at clouds. In my younger days, I still had hair. So I don't know, for operational purposes, whether commercial cloud is viable or not. Different projects have come up with different answers to this question. But for what we do, for things like developing research software, the cloud has absolutely killer advantages. So for example, if Jonathan here wants to see if his algorithm can scale to 100 nodes, he's not going to get 100 uncontested nodes, not at CHPC, not at ILIFO, not anywhere. But on Amazon, we can rent them for 1 hour for a very reasonable price and do our experiments. So this kind of thing is superb if you're developing software, and costs are quite easy to estimate, right? Unlike something like a LIFO, I don't know, well, Rob probably has the numbers of how much a LIFO costs overall, but for me, I don't see that, but for the cloud, I can tell very well how much a given experiment is going to cost. So our relationship of our software development efforts with respect to the cloud, what we found is that running cost effectively on the cloud requires you basically to make your software better. It requires you to solve all these problems. And so the cloud for us is almost like a self-imposed honesty-keeping mechanism. And I will postulate that a software stack that can be reasonably effectively deployed on a cloud will actually be highly efficient on any other architecture. So that's kind of the scope of our project, the Africanus project. You could say it's about how do we deploy these mad Rube Goldberg machines on the cloud in a reasonably efficient and scalable way while relying only on open standards and hiding the mess from the users. And why do we bother with this? Well, like I said, I'm still on the fence whether we want to process Meerkat data on the cloud at scale or not. But, well, first of all, it's made our software a lot more efficient. Second, it democratizes the compute and the data reduction, right? At least anyone can get on the cloud, right? For some money. And we've been quite successful with it. So if you missed the 3 posters this morning, I'm very sorry for you. But Simon, Landman, and Jonathan are an audience here. If you ask them nicely, they might show you the software pieces. I'm going to talk about the last piece of that technology, which is the workflow framework. And it's something called Stemela, which Spe, who is not an audience, is he? Started developing for his PhD originally in 2018. So the idea was basically, let's use Docker and use Docker containers to express our workflows. And a couple of years ago, we started kind of a next generation rewrite of this thing, which I'm going to talk about. And so we rewrote Stemela, but we do not, the philosophy is we do not rewrite any software packages. We domesticate them, like your dog. And if you're in a business, you know there's a lot of feral software out there, so domestication is not easy. So how we domesticate software, basically you take a wildcat, you put it in a box, right? A box is something we call a cab. A cab represents an atomic task in your workflow, so it could be wsclean, it could be a Casa task, it could be a snippet of Python, whatever. And what you do is you provide a piece of YAML that defines what your cab is. And that YAML defines a Docker image and possibly a registry. So it could be the LIFO registry, could be. But it doesn't actually have to be a container even. You can run a native binary if you want to. You specify a command to run, and you specify input and output parameters. And there's this very rich typing syntax which Python provides, which lets you describe basically the parameters of the task in a very flexible way. And Stemela takes care of kind of validating the parameters, making sure the steps match up, and so on and so on. And we now have a collection of standard cabs for most radio astronomy packages that you're likely to need. It's called Cult Cargo, so you can Google it, you'll find it. And you can write your own. You can easily roll your own. So that's one piece of Stemela. The other piece is a recipe. So a recipe is basically, it's also a YAML document, and it represents a sequence of steps. And each step can be a cab, so an atomic task, or it could be another recipe. So this thing is kind of modular. You can have recipes all the way down. And you've got this concise YAML syntax for specifying the sequence of steps in the recipe. It's composable. You can invoke recipes from other recipes. You can have conditionals. You can have loops. You can have scatter-gather, so you can run things in parallel. And if you look carefully here, you'll see there's a formula language which basically lets you cross-links the parameters between the steps and do all sorts of wonderful things. It's composable, so we've extended the YAML syntax with an include statement and the use statement, so basically you can have libraries of YAML files which you can include into other YAML files. And I'm actually going to come back to this slide after I've shown you the other ones because it gets a bit complicated. So the flagship applications of this right now, the first things we worked on with Stemela are something called the Parrot pipeline. So it's a self-calibration and imaging pipeline which John is kind of developing now based on earlier work from me. It's essentially has become a unified pipeline for Meerkat and for the IAU. So we're getting breakthrough funding for this project because we want to do interferometric city searches. On the back of that, we have a pipeline called Tron, which does fast imaging and transient detection. And just to give a plug, I'm going to have a poster on this on Monday morning. Come see it. I've got some wonderful results. This thing is moving so fast that when I submitted the abstract for the poster, I didn't have any results. But now when you come to see the poster, you'll see a lot of very cool stuff on it. We've got some custom imaging pipelines. For example, Athanasius here has developed one for reprocessing the Galaxy Plane Legacy Survey. And the proof of the pudding here is that these pipelines, we've deployed them locally on the Rhodes cluster, we've deployed them on Amazon, on the cloud, right? We've deployed them on LIFO, we've deployed them on Oxford cluster, on the Pleiades cluster in Italy, at the university, at Berkeley. So this thing actually works in a platform-independent way, and I will show you how in a second. I just wanted to contrast the approach of writing recipes versus scripting versus, there's something in fashion now called data flow programming, right? And that's been, on a low level, that's been popularized by Dask. So data flow programming is when you programmatically construct a graph, which represents your computation. And so Dask does this at a very low level, but you also see a lot of use of this for high-level things like workflows. So you've got this containerized CWL, what's it? Containerized workflow language. There's a project in Australia called IAU GA, which is applying something similar to SKA. So you have graphs of high-level tasks, and that's how you describe your workflows. So this is quite cool, because if you have a graph, then a graph is amenable to automatic optimization and scheduling, but it's not a very human-friendly way to develop workflows, right? If you ask an astronomer to write a pipeline, an astronomer is going to write a script. That's because linear scripts are, compatible with the human brain, and even a casual, non-professional programmer can script in Shell or on Python or whatever. But once you start deploying a script on a cluster, scaling up, invoking the scheduler or whatnot, that all becomes kind of manual and becomes platform-specific, right? So Stemela kind of aims to be in the middle of the spectrum, right? Your recipe is still a linear sequence of steps, so it's like a script. It's kind of easy for a human to follow, and the syntax is quite concise. But underneath, under the hood, Stemela turns this into kind of a more graph-like construct, and then it's actually able to schedule tasks on Slurm or on Kubernetes. So this is how it gets to be a platform-independent deployment framework. So what it looks like schematically, like if you're running it on your local machine or on your local cluster or on a node, you SSH into the node. You go into your directory wherever your data lives, you've got your recipe, you say Stemela run recipe YAML, and you give it some parameters, whatever the parameters of the recipe are. And off it goes, it talks to the container registry, it pulls down the images which are required to run your workflow automatically the first time you invoke them. And everything runs, and you get outputs in your local file system. Now, if you want to run this on Amazon, things get a lot more complicated under the hood, but what you do on the command line is you say Stemela run exactly the same thing, but you give it a separate configuration file, a separate piece of YAML, which tells Stemela how to deploy your workflow. That YAML is probably given to you by someone, well, whoever configured your Amazon cluster for you. And that tells Stemela how to connect to the cluster, how to talk to Kubernetes, where the data is, how to run the recipe and whatnot. But for the user, everything is the same. Same thing for a local cluster. Again, your system admin is going to give you a configuration file, and that talks to your local Kubernetes cluster. And same thing for Slurm. So this is a bit of anecdotal evidence. When I decided it was time to run this thing on LIFO, it took me about half a day to implement Slurm support. And it worked remarkably well. And this kind of proves my point that if you force yourself to do things efficiently on the cloud, everything else becomes easy. Supporting Kubernetes was a lot of work. Supporting Slurm was half a day of work, which is great. Now, taking you back to that complicated slide I flashed up briefly, this is how it looks like when we run this thing on the cloud, right? So you've got a local instance, or this could be a local machine or a cheap virtual machine instance on which you run your Stemela session. Stemela is lightweight, right? It's just Python. It doesn't consume any CPU. So this can run on a very small instance. That Stemela session then talks to your Kubernetes cluster, and Kubernetes on the cloud has this wonderful property of auto-scaling, right? So you run let's say your main application, like Quarticle, you start it on a small cheap instance, and then the application tells the autoscaler, I'm going to need 1,000 CPUs here. And the autoscaler says, well, okay, I need to provision 1,000 CPUs, so I'm going to need to spin up some expensive instances. So the autoscaler spins up those big expensive instances. Your application runs, assuming it's it can take advantage of 1,000 CPUs. And then when it's done, those things are brought down in an orderly way. So the bottom line is these expensive instances only exist pretty much for as long as you're running your massively parallel application. And when you're done with the massively parallel application and maybe you're moving on to another step of the workflow that's serial, it goes back to running on cheap instances. So this is kind of the key to keeping costs down on the cloud. The other key, of course, is using S3 object store as opposed to block storage. So that's actually pretty much, I'm about finished. I'm going to tell you where we're going to take this next, where I see some killer applications of this. So first of all, there's a paper series on this coming soon. I think very soon, I hope very soon. Come see posters 1, 2, and 3 in the past, or come speak to Simon, John, and Landman about them. The first thing I'd like to do with this is have there's a lot of imaging competitions in the literature where people write an imaging algorithm and then they publish an image and then they say, well, my image is better than the competitor's image. And that's never very meaningful because then the competitor gets upset and says, well, you weren't running my algorithm correctly. So these things, historically, they've never worked very well to compare things. So what I want to do is we've got the raw data for this famous radio galaxy of Mpati from the first open time call. So this data is public by now. Amazon has a program for hosting public data for free. So we've already deployed this data set, this raw data set on Amazon. What we're going to do is we're going to deploy an end-to-end similar recipe, which basically starts with the raw data and takes it all the way down to a final image. And then, presumably, you can run it yourself on Amazon or on your own hardware. And then, if you're saying you've got a better imaging algorithm, well, you modify the recipe, you stick your own imaging algorithm into that, and then you publish your recipe. And then maybe we can have a recipe contest, not an imaging contest where just the final products are shown. And where this moves us, I think, is towards full reproducibility, right? Because you don't just publish a paper, you can actually publish the full set of recipes that went into it. And I've tried to show the set example here. The paper I've got on our first transient detection actually comes with a full set of recipes, which are hopefully rerunnable. So yeah, I mean, in conclusion, passengers welcome. Here's the link to the Stemela project. Please feel free to get in touch with us because we love users and we love helping users. So thanks very much.
Thank you, Oleg. Any questions? Guess everybody just fully understood it. Oh, there is.
Yeah, thanks a lot for this wonderful concept and the development since I left actually. One question, since we are talking about competition or competitions, is there any or are there any measures to compare these images that you're planning also for this deployment? I mean, measures that you can compare the results with. I mean, any quantitative measure that defines the quality of the imaging of a pipeline?
I would rather avoid that question because I think what this allows you is to actually duck that question, right? Instead of writing a paper where you say, right, my algorithm has dynamic range of X versus competitor having dynamic range of Y, you can have the results, right? Here's the image, you can run CART on it, you can view the image. You can decide for yourself if image A is better than image B, because that answer is going to be different depending on who you ask, right? But at least this way it's fully open, reproducible, and people can make up their own mind. So I'm sorry, I've ducked the question, but that's because it's a very difficult question.
Yes, full reproducibility requires version control. Do you take account of version control?
Yeah, so the images in the registry are all versioned. So as things get updated, and I can send you a preprint of the papers when we submit them. We've put a lot of thought into how you could actually sign a workflow with all the version numbers that went into that workflow. So in principle, if you're only using container images, if those images are maintained on a public registry, you can have a signed workflow which gives you, theoretically bit perfect. Of course, as you know, things are never bit perfect because parallel algorithms can give slightly different answers depending on sequence of parallelism. But yeah, versioning is in there.
Okay, I think we have to move on, sorry. So thanks Oleg. So our next speaker is Thomas Dudkiewicz, I hope I said that correctly. Dudkiewicz, okay. Another talk about cloud.
All right. Good afternoon, folks. I'm Thomas Dudkiewicz. I'm here on behalf of the Space Telescope Science Institute, and specifically of the Mikulski Archive for Space Telescopes, to talk to you about what we've been doing on our side of the pond with cloud platforms. So to begin with, I'm going to do a very quick introduction to who we are, to Space Telescope and MAST. Please don't read all of this, you don't need to. The basic summary is that Space Telescope Science Institute is the Science Operations Center for Hubble. We are also the Science and Mission Operations Center for JWST. And Roman, when it launches in, hopefully, October 2026, we will also be the Science Operations Center for that. MAST, the Mikulski Archive for Space Telescopes, is the primary archive for all three of these missions. Now, at STSCI, we have these key strategic goals, and I really just want to draw your attention to this one, which is make the world's astronomical information accessible to all. And working in the archive, we really think about this a lot. And when we think about the word accessibility, there's more to it than just the literal definition of people can access it, right? Anyone can throw data up on a server somewhere. But there's a bigger picture of how do people access it through APIs and through search forms? Are those search forms usable by people who are blind and low vision? You know, is there good documentation and tutorials? Are we doing outreach, right? Accessibility is so much more than just, oh, I put the data on a server and you can go get it. And I keep this in mind because this is kind of the core theme of what we've been trying to do with platforms. And the reason why we've been trying to do things with platforms is because things are about to change, at least for us, in the optical band. We are primarily an optical archive, and so some of the stats here I'm sure will not impress any radio astronomers in the crowd, but for us it is a big change. So the context. MAST, as I said, we are the archive for Hubble, JWST, and TESS. There's also other missions like TESS, Kepler, Pan-STARRS, GALEX, the International Ultraviolet Explorer. We have 20 plus missions in the archive. We also serve the community with high-level science products. So this is when scientists come back to us with something that they've analyzed. And I think a good example of this is someone who reprocessed all of the TESS light curves by doing a cross-match with Gaia, and they were able to significantly improve the quality and the depth to which you could detect exoplanets. And our public data are accessible to everyone without regard to national affiliation. So anybody can get to the data that is in the MAST archive. And right now, all of that, all of the missions, all of the community contributed science products, that puts us up at about 4.3 petabytes. And again, the radio astronomers in the crowd are probably chuckling because that's just pebbles to them. But what's about to change for us is Roman. Again, as I said, plan to launch October 2026, and the data is going to be of unprecedented size. We were preparing for 20 petabytes of data, and they built the telescope so darn well that it's going to slew and settle really fast, and it's actually going to be 30 petabytes, which is great news for science, and we're very excited. But on the archive side of things, we have some work to do. And really, just to give you a sense of this, the Hubble Space Telescope, one of the most scientifically productive instruments ever built, over 30 years, has produced 172 terabytes. Again, we are expecting 30,000 from Roman in the first 5 years. So this really is a revolution for space optical astronomy. And then the question becomes, as the archive, how do we actually make this accessible, right? It is obviously insufficient to put 30 petabytes of data on a server and say, have fun. And so our answer to this is cloud. And I'm not going into the details. I think some other presentations have covered this pretty well, but our idea of what accessible to all means is using cloud platforms to do these kinds of things. And so here's our definition. This diagram is kind of a nice looking diagram to show you all. but it sort of covers the basics, and I think it's nothing revolutionary that you haven't already heard in some talks today. The basic pass-through is that users on a browser go into Jupyter Hub, that deals them out a Jupyter Lab session, and within this environment, they have access to the public science data, which is that 30 petabytes. They have notebook tutorials that teach them what is an ASDIF file, how do I open it, how do I do basic data analysis, and then also the pre-installed software, so basic packages that you would expect to use, and then we allow you to create your own containers and install things on there. We also give you persistent user files. Right now, for the platform that we currently have, it's about 25 gigabytes, but that might change over time. And then we also give you access to the broader internet, so you can pip install, query other things from Mast, push and pull things to GitHub. This already exists. So again, this screenshot here is from the Tyke platform, which we've done with test data. It's not nearly as big as Roman is going to be, but it still produces somewhere on the order of 10 terabytes every month. And that's not including all the HLSPs that people then contribute back to us. And so we end up with a lot of data. And so this was sort of the test case for science platforms. Could we make this work? And the key thing that we're trying to avoid, and we're trying to get our users to avoid, is downloading things, right? Again, I've said 30 petabytes a lot, but that is such a huge volume of data that it's, one, not feasible to transmit over the internet, and two, not feasible to expect people would have the disk space for that. If anybody in the audience has a petabyte hard drive, I'd love to see it. That'd be so cool. But that's just not where we're at right now with the technology. And so we're trying to move away from that workflow. You'll have to indulge this GIF, but this is a movie that I used to really, really enjoy. At the very end of the hit 1985 film, Back to the Future, Marty's concerned that there's not going to be enough room to get the DeLorean up to speed so they can travel back to the future. And he says, the doc in reply to him says, roads, where we're going, we don't need roads, because he's in a flying car. Well, downloads, where we're going, we don't need downloads. And this is what we're trying to get people to come around to this idea that things are going to change for their workflows, but not necessarily for the worse, that we can do interesting things with this. And so our vision for platforms is exactly that this can be something that's exciting for the community, that empowers people who haven't been able to do astronomy before to do it. So this is our core statement, right? Keep it open, keep things accessible, and keep them responsive to the community. And as a demonstration of what it takes to get access to our platforms, I've got a little diagram for you here. Step one, use a valid email to create a MyST account so we know who to give stuff to. And step two, log in. That's it, and you get compute for free. And it's about the processing power of a modern laptop. I can run things on both, and it's roughly about the same speed. And that's all you need to do. We don't care what that email address is. We don't even check if it's a real email. Please don't use a fake email, though. We do, on occasion, have to email you if you run out of storage or other things. And this really has the potential to unlock computing for everyone. You don't have to have a PC. You can go to your local library and log in, and as long as they have a browser and a semi-decent internet connection, you can do things. I was running demos downstairs today and pulling through gigabytes of data, and it didn't matter because all of that processing was happening in the cloud, and all it had to do was transmit things back and forth to us. So I think that really is a big change for the way that people have done astronomy in the past. So where we've been, where we're going, what we've done so far, you have to start with the documentation and the tutorials, but this is obviously insufficient, right? We have to write it all down, but it's not just enough to say, here's how you use this tool, come use it. We have to actively seek out people. The first part of this was doing a joint workshop between MAST and the TESS mission office at the American Astronomical Society meetings. And this made sense because we wanted to work closely with the TESS mission to design a platform that would work for them. We've also recently did a summer webinar on this, and so it was an interesting way to use the cloud of having me plus 30 other people from around the world simultaneously log into this commercial cloud instance and all work together to go through exercises. These were 6-hour-long sessions on a weekly cadence with 3 time zones. I did them all. That was really terrible. I will not do 3 time zones on one day again. But there was a lot of interest in that kind of stuff. And so we know it's important to reach our users, not just in the US, but around the world. And this is a quick screen grab of it. So this is what it looks like using the platform, producing a plot here. Here I am in the upper right-hand corner saying something interesting, no doubt. And all of the recordings for this are available at this link here, and this QR code will just take you there. But the community impact on this was enormous. So there were 150 participant hours, that's how I'm measuring how long people were actually engaged and joining in the sessions for in the live sessions, and 77 hours of people watching the recordings as of yesterday when I was touching up this talk. And so the takeaway is that we're definitely going to do this again. And the way that we do it, the cadence, the topics, the time zones is still TBD as we process feedback from the last one. But this is a great way to reach people. And then very quickly, I'll wrap up here with our goals for where we'd like to take this. So there are a few new features that we'd like to release. One of them is Teams, and this is a pretty intuitive concept: shared compute, shared storage of files. So you can imagine working with your research group. You can also imagine working in a university context with students and assigning labs and doing things like that. And in fact, we actually have supported that. There have been a couple of people in our local area who have reached out and said, could I do X, Y, Z? And we spin up some instances for them. So if you're interested in that, please come talk to me or stop by the Mass booth and we can work that out. Real-time collaboration, imagine Google Docs or Word Online, but it's a Jupyter Notebook, which I think would be extremely cool. It takes that collaboration up to the next level. Batch processing, so if you have a job that's going to take 48 hours to run and you can't run that in a Jupyter Notebook, adding some support for that. As I mentioned, we'll do some additional virtual webinars. We're going to try to take the traveling or the joint workshops on the road, and any other ideas. Part of the reason why we're here is, again, the platform needs to be responsive to the community, and you are the community. Again, the core idea of this talk is making astronomical information accessible to all, and that means everyone sitting in this room. So we would love to hear what you have to say. With that, I think I will open it up for any questions.
Any questions? Start here.
Ooh, so many questions.
Oh, that was a great talk, thanks. I think you're absolutely right. No one has the capacity to move 30 petabytes around the world trivially. But I do worry, say I'm involved in projects with HST where we've reanalyzed the whole archive because it's so small. That's now going to be fairly infeasible. And there's that phrase, trust but verify. It makes it very hard if someone produces a shape catalog with, say, Euclid or Roman data, that there's basically de facto or, de jure just one catalog. No one else in the community almost has the compute capacity or the tools they need to actually check whether those results are valid. And that idea of having parallel efforts kind of goes away. And that's a bit of a big problem, I think, in this next phase. So what's, I guess, your thoughts on that?
Yeah, I mean, it is a big problem. And a core part of the advantage of the cloud, I think, as we've seen in some of the other talks, is the ability to reproduce or that kind of thing. When we think about it from the archival perspective, I mentioned those higher level science products. And so there is some plan to support those in the cloud. So if you're concerned about, well, what happens if someone else wants to reproduce a catalog or use this? You could imagine accessing our cloud, accessing our storage, creating your own higher level science product, and then saying, MAST, this is a community service, will you please host this? And there are plans for us to move in that direction and support that kind of stuff.
Hi, great talk. How do you anticipate managing resource allocation for your users?
That's a great question. At the moment, we don't. What we do is everybody who logs on to Tyke gets the same thing. Again, it's about modern laptop, 25 gigabytes of storage, 16 gigabytes of RAM. In the future, with Roman, the plan is to open it up for proposals. So you would say, I have this use case, I need this much compute, please give me the extra power.
Hi, thanks for the talk. Just wondering how you're going to sort of budget for storage of 30 petabytes of data and the data egress costs, presumably mostly from visualization.
Right, so at present, we're part of the AWS Open Data Bucket, so that is fortunately free to egress data out of. So we're not too concerned about that, but you also, the visualization aspect of things you were? Yeah, I think, so I don't actually work on that end of things, and I know, I'm not sure which tier that they've actually selected to store that data in for long-term, or whether they'll cleverly put some things in Glacier and look for the things that are most frequently accessed in like a higher tier. I'm not sure what the platform team has done to make that accessible over the long term, but I know that they're thinking about it. So sorry, I can't give you a better answer.
Hey.
Hi.
Thanks for a great talk. We're certainly in the era in which we can no longer bring the data to the user, but we must take the user to the data and offer all the capabilities that they'll need to do their analysis and so on. I was wondering if you host proprietary data and how you go about serving that out. Is that more than just the email sign up and that procedure you outlined?
Yeah, so at the moment, we have exactly 0 proprietary data in the cloud for that reason, because it's a rather tricky thing to handle that authentication and making sure that nobody gets access to something that they're not supposed to have. And so for survey missions like TESS or Roman, it's less of a concern, but at some point, I think there is a need for us to allow that kind of access. HST and JWST will be in the cloud, and how we handle proprietary is still uncertain.
Okay, this is a cheeky one. I've been in this business for a long time, and I've worked a lot of centers with very large computers connected to very large networks. And I just wonder how you're going to handle it when the script kiddies figure out that you're not checking email addresses, take your system down, steal your IP address, and attack the Pentagon. Because I can tell you, getting a phone call from the US government at 3 a.m. on a Sunday morning is not fun.
Mm-hmm. This is something that I think keeps a lot of our developers and a lot of our scientific leadership staff awake at night, and having nightmares about someone deleted the entire HST cloud archive, or someone hacked our cloud and used it to attack Europe, and now it's a diplomatic crisis. And I wish I had a quick and short answer for you, but frankly, I don't. There are security measures in place. Don't go on the platform and try to mine Bitcoin. We will know. We do monitor the platform to some extent. But no, you're right. It is a concern. How do we balance the idea between let's make this open to everyone for any purpose, and also let's make sure that it doesn't get used for nefarious purposes? So my answer is we're thinking about it. All right. Thank you.
Final talk this afternoon is Amelia Bayo, and they talk about some schools and data science.
And I'm shorter. Okay. Well, hello, everybody. Thank you for staying until the very end. Yeah, my name is Amelia Bayo. I'm an astronomer at ISO, but in fact here I'm not really ISO. Well, ISO is paying for my trip, so I am ISO, but I'm going to be talking about something else that ISO is not particularly involved in. That is 2 initiatives. Sorry, I don't know. Yeah, I don't know about the mic. So 2 initiatives to, in fact, bring astronomy to the new generation and bring data science to the new generation. And one of them is La Serena School for Data Science, and I'm going to be talking mostly about this one. And I feel quite like an imposter because, in fact, one of the instigators of this school is Guillermo Cabrera, that he was around here before. And one of the current persons that allow us, in fact, to have this is Dara, that is here. So I don't know why I'm talking about this, but I am talking about this. And then I will also briefly talk about the Spanish virtual observatories. As you can tell, I cannot say Spanish. I have to say Spanish because I'm from Spain. So let's go. So when we started doing La Serena School for Data Science, and this started quite a while ago, I was still a very young, naive postdoc that hadn't been taught about pedagogy and how we learn about things. But it turns out that a lot of it, I mean, you have to be taught, but a lot of it is also very intuitive. So I had no idea about this multiple intelligence theory. And depending on what you read, you may find like 5, 9, whatever. But the bottom line is we learn in different ways. But yeah, we have to understand that we learn in different ways. And we can use many different tools also to transfer knowledge, right? And the way to capitalize on that is, in fact, through collaborative learning, so that we can take advantage of the many different ways that the different students, persons learn. So, I'm sorry, this is really annoying. So, okay, if you look around, as I said, you may find different versions of this, but I have like paraphrased a bit the one with 8 basic competences. And just by chance, in fact, we were pretty lucky because without knowing about this, in the way we designed La Serena School for Data Science, in the way we operate La Serena School for Data Science, as a happy accident, we do cover quite a number of these competences. So you will see, well, this one was easy doing, yeah, sorry, I just think that then, I'm not going to be heard, but okay, perfect. In fact, normally I don't use microphone. I've been the whole morning doing outreach in schools and I just scream because also I'm Spanish, so yeah. So, okay, we're doing astronomy, so the part of interaction with the physical world, again, right? We are doing something that is very related to the physical world. The way we do the school, and I will explain it a bit better, it potentiates, is that the word? Yeah, it moves forwards personal autonomy and initiative, and we do that in an active way. Linguistic communication may sound like, okay, we're talking about astronomy, that doesn't make a lot of sense. For you people in the US that are used to speaking in public, that may not make a lot of sense. For Chilean students, and this is a school with Chilean and US students, it makes a lot of sense that we put a lot of emphasis on how to communicate, because in fact, I was not aware until I moved to Chile, but for a Chilean student being put in the blackboard explaining something is a punishment. I mean, it's not something that you do to learn, it's a punishment. They put you there to ridicule you. So we really have to change that. Mathematics, again, learning to learn, and informatics, and cultural, because as I said, La Serena School for Data Science brings together Chilean students with US students. Within the US students, we try to have a representation of very different universities, and we are lucky enough to also include other Latin American students. So, more or less around 2012, probably even before, but I got only involved in this in 2012. I was at that point leaving Chile, in fact, but with the idea to come back to Chile, and there was all this thing that, you know, big data in astronomy. So we are going to have LSST at some point. We are going to have all these fantastic radio interferometers, and Chile has access. Now I go back to LSST, has access to LSST, right? But there was no culture whatsoever of astroinformatics in Chile. And there was this really great proposal that was put to bring together experts from the US and from other countries to teach the new generation all the things that they were not being taught at university. So it was, since the beginning, very clear that this needed to be interdisciplinary, so we were not going to target only astronomy students, but we were going to put together to work. At the beginning, it was only computer scientists, astronomers, and statisticians. Then we grew, and there is Guille, so again, I don't know why I'm talking about this, you should be talking about this. And the kind of learning, we wanted to be super practical. We wanted to be project-based, and again, very collaborative. So La Serena School for Data Science was born, and the mission statement is we want to introduce advanced undergrad and early grad students to the world of multidisciplinary data science. Easy, very small objective that we had. So one great thing that has to do also with accessibility and with inclusion is that the program is a 10-day program that is fully supported, fully economically supported. So every student that gets selected, they don't have to pay anything. They come to Chile, they go to Chile, we're not in Chile. They go to Chile, they spend 10 days working with their peers and with the professors. And we have a big NSF grant that covers a lot of it, but also there was a lot of effort, and there's still a lot of effort by the Chilean team to get all kinds of other sponsors that allow not only to have more or less half of the students Chilean, but also to have people from Ecuador, people from other Latin American countries that they normally don't have access to this kind of education at all. So, La Serena School for Data Science was born, and now we have the problem of success because we have a lot of applications. So, normally we have 30 positions. That's never true. We always manage to put more, but we aim for 30, and we get hundreds of applications. And we want to be inclusive, right? Like, how do you do that? Because it's not easy at all. So we want to focus on 3 different aspects. So gender, with a still quite simplistic version here, but okay, with gender, disciplines, and institutions. And this has been really a major problem, how to balance all of this. And in the selection committee, we are quite a few different people with different opinions and different ways to try to move forward. I think what we did this year was a pretty good thing, is we had a set of criteria. So we had grades, of course, but they were defined with a taxonomy, let's say. So we had a lot of words that allow us to determine what kind of skill we are trying to take and what kind of impact we are trying to get. And for instance, some of the discussions that we have is that, in principle, we don't have students that already have access to this knowledge, not because we don't want them, but because we want to give the opportunity to others. So we do get into a lot of trouble of people contacting us, our colleagues, and saying, why don't you select my student? He had a wonderful application. And it's like, yeah, I mean, he knows the whole curriculum. So no, we are not selecting them, okay? So in terms of gender, as I said, we are doing somewhat fine, not as fine as we would want, but we are doing somewhat fine. In terms of the majors, so here we do have a big issue. So in 2018, we expanded to also biomedical, mostly image processing students, but we clearly have a bias. We clearly reach much better students from physics, mathematics, and astronomy, just because most of the professors, the people that we are running the school, are from those backgrounds. And we have a lot more problems finding bioinformatics and medicine students. Also, because when we are targeting master students, we are very used to think about astronomy and somewhat computer scientists, that they are fully academic master students. The bioinformatics, at least in Latin America, they are not fully academic master students. They are working at the same time, so they cannot take 10 days to go to a school as easy as the other one. So this is a problem that we are dealing with, but it's like the first part of a problem is to be aware that you have a problem, so at least we know that. How do we work? So the way we work, as I said, is like more or less 10 days, at least when we have the in-person, we have the in-person school in La Serena. And what we have is like a gradual switch from first having some lecture, but always together with hands-on sessions. And the way we do these things is normally with Python notebooks, where you have the lecture in the Python notebook, and then you have exercises with either mistakes or parts of code that are missing, and the students have to go through them immediately or during the lecture or immediately after the lecture. And then we start to transition to have project time. So at the beginning of the school, we present projects to the students. Very often they're open-ended projects, and we make groups of 4 students where we pair hopefully one astronomer student with one computer scientist, with one bio, with one statistician. We do not always manage to do that, but at least we don't want only astronomy students. And also we pay attention that at least there are 2 and 2 in terms of nationalities. So we start with just a presentation of the project on the very first day, and then we start ramping up the time that they have to work on the projects and decreasing the time for lectures, so that the last 3 days they are only working on the project. And the professors, I really have to say, like the faculty, we have been very lucky. The faculty are extremely enthusiastic. They spend the 10 days there the whole time with the students. And we have had a lot of really nice collaborations. People, I mean, I still have a lot of contact with the students from the 2013-14 edition. So this is really great. In terms of the lectures, well, we start from very basics. The principle of the school also, it was never since the beginning to be a very specialized school. It was like, we're going to show you a lot of tools. We're going to show you a lot of examples. We don't expect you to understand everything to the latest detail. We want you to understand that these are not black boxes, that you should then go to the details if you're going to use them, but we're going to expose you to a lot of them. You may agree or disagree, that's perfectly fine. I think there are other schools that are a lot more specific for specific topics, but what we do is we offer them a very wide range of topics. And 2 things that are, well, the first one, good and bad. At the beginning they hate it, and then they really like it, is that every day they have to report on the project. And they have to switch who is the speaker person also, because at the beginning we had always the US person being the speaker person. It's like, no, we have to switch around. And it's really I don't know, I may sound very naive and very stupid, but for me, it's really, really refreshing and really, really good that you see the change in the Chilean students particularly on when they have to report the first day than when they have to report the last day. It's really, just giving 10 days of you have to explain what you're doing to others can make a huge difference. And then this, everybody loves it, of course. We take them to the telescopes, they spend quite some time there, stargazing, and they just love it. Of course, you all know that something happened, right, not so long ago, and everything had to go virtual. So we did go virtual, of course. And this had, I mean, it worked. I was surprised that this did work. It did work. It was not the same thing as in person, that is absolutely true, but it did work. What we did is we included PAs that then we have kept for the in-person edition also now, because we really needed, we were in different time zones, we really needed people. Sorry. We really needed the different time zone support because everybody was at home. We had synchronous and asynchronous sessions, and we were using just a simple but surprisingly powerful combination between Zoom, Slack, and GatherTown. And these are just, the typical pictures that you have to put of all the virtual meetings that we had. Something that I really want to highlight is because we have this, I really think the National School for Data Science is very special. It's very intense, and we do have a very personal relationship when we do it in person. We were all very worried what's going to happen doing this online. I mean, this cannot work. And the LOC, Guillermo, Danke, Valeria, they're just fantastic. They created these boxes that they ship everywhere, and we didn't even know. So they surprised the faculty also, where they had all kinds of things like, of course, the book and some like memory sticks, whatever, but they also have some chocolate, like when we take chocolate everybody together, and when we do coffee and blah, blah, blah. And it was really nice, and it really generated a feeling of belonging. It really felt like we were all together working on this. Things that we did, and that we have tried different times, and that didn't work, just in case you want to do something similar and you want to avoid some headaches. So we did, and particularly Pablo Protopapas, he prepared a lot of material like preschool coding bootcamp. And that sounds like a very good idea, and we were very pro it. But the thing is that you cannot guarantee that everybody's going to have the time to follow this, right? And normally we do have many different levels of coding experience and things like that because of the nature of the students that we have. But when you do this, you just even increase that. So this was decided not to be done this year because, in fact, it created more problems than it solved, really, because then the roles of who was going to code were too hard-coded. So it was not easy to get people that were not so used to coding to actually code things within the school. We did have at the beginning a lot more specialized lectures where we went into the details. The thing is that you have to choose. You have to do one or the other. Either you go into all the details of specific topics, and then that's one kind of school, or you go into a more general school with many tools. At least we couldn't do the two things. And in fact, these lectures turned out not to work at all with the rest of the school. So we decided not to do that. But we have always some optional lectures, and in fact we encourage the student to ask also, if you are really interested. Before we had natural language processing, the first time that we had it was because some students asked for it. It was not in the curriculum, now it is, but it was not in the curriculum, some students asked, so we created a special lecture on that, on the fly. Something that we had also is that for a few, when we were doing these more specialized lectures, of course, we had teachers, professors that were coming and going, and that doesn't work, at least not for this school. This is a school that is very hands-on. You do need time for the kids to warm up to you and then come to ask you things and everything, and if the professors are changing all the time, then that doesn't work. And you also need professors that are very used to a multidisciplinary environment, so that when you go to a group, you don't expect to have the very specific clear question. You expect to have like a blah, and then you have to make them talk to each other, and you have to understand what they really need. So you need professors that are used to multidisciplinary work and also very present. The pre-recorded material and notebooks, this is not that it didn't work, it's that we suck at it. We are really bad at preparing before, so we should have this, but we just never managed to have it updated. So this is not that it really, yeah, it didn't stick, but that's our bad. That has nothing to do with it not working. We've been doing this for quite some years, so we have some testimony that explains how what they learned during the school was fantastic for the future. A lot of them, they still keep friends from the school, so that's pretty great. And I just put this one from Josh, that when he went back from the school, what he did is he replicated it at his university, and that is exactly what we were trying to have students that they will have the commitment then to replicate what they have learned. So switching gears, very, very different. So the Spanish Virtual Observatory started the schools, in fact, these schools of 2009, they started even before, but as part of the EuroVO project. They started in 2005, and I know because I created one of the cases for that, for that school. It is very, very different in the sense that what the SVO and the EuroVO project and Escape, what they are based, they are very short schools, so very few days, and they are focused on the training of how to use tools, not so much to create your own tools, but to be aware of the tools that already exist there, with predefined and closed science cases, because it's a small amount of time. The diversity, how they tackle diversity, this is really interesting that we cannot do. In fact, we have had applications of amateur astronomers, but because of the way we have applied for the funding and everything, we cannot cover that. But in the Spanish Virtual Observatory, they do have open call for professional and amateur astronomers, so they are showing amateur astronomers also these kind of tools. They started like very local, and local meaning Spain. And then also because they joined forces with EuroVO and Escape, they have also done other schools around Europe mostly, but then also since 2020 when they became virtual, they also target Latin America. So they also have been doing schools in Brazil and in different places. And they have done many, many schools, and normally they were targeting 20 to 30 participants. Then when the pandemic hit and they went into virtual, they are doing that a lot more open, but still there is a registration process and everything because they found that it didn't work if it was fully open. I mean, you couldn't have engagement. And I just love that our previous speaker talked about accessibility, because in fact, as I said, when we started this school, we didn't have, at least I didn't have the necessary training to understand how to teach in different ways. And then also something that I didn't have at all, we were using Python notebooks all the time, and we were never, at least I was never, and I think I'm more conscious about these things than others, never checking if our notebooks were accessible with a screen reader, if all the images that we were putting have alternate text, all these kind of things. We were not doing it at all. I'm not going to claim that I do always perfect now, not at all, but at least I'm aware of these kind of things. And sometimes it's very simple things, right? Can you incorporate alt text in anything that you're doing? AI is fantastic now even to include these alt text. Just check that it's not saying something stupid and just incorporate it. Using tactile material, I don't have it here, but we did create it in Chile some tactile material to explain star and planet formation. Okay, you will say, what does that have to do with astroinformatics or something like that? Well, there is a school in Santiago where one of the teachers that is just fantastic thought how to explain a CCD to blind kids. And I'm going to take my time to explain this because it's just great. So basically you have a kid that is the star, and the star is throwing photons, that is just little balls, and little balls with different textures. Then you have a kid that is the CCD, that is just getting the balls. And a kid that is the electronics, that is basically transforming the ball that is getting into the little buckets, is counting how many electrons are coming to the different buckets and transforming it into something else. It can be with Rayleigh, it can be whatever. And because the balls have different textures, you can even end up with a multicolor image. I mean, I think this is fantastic. I think it doesn't matter also if you are fully sighted. You can learn so much if you think about explaining even electronic things in this way. So, yeah, whenever you put material out, again, is your online resource accessible for screen readers? are your menus well done in the sense that you can access them with rotor? I don't know if you if you guys are aware of what rotor is. So basically, in any server, if your menus have real structure and the metadata is proper, then the blind person doesn't scroll down. It just goes through the menus and can access whatever part of the web page is without scrolling the whole web page. Right? And again, all of these are things that you can find. There is a lot of documentation that you can find, and just switching the way you put your metadata makes something accessible for a blind person or absolutely a nightmare because they have to scroll down and get toggle, and there is not even description of what the toggle thing is doing, right? So yeah, sorry that I took the time to preach here, but I think this is important. And also, I don't know if you're aware of this Afterglow resources, but they are really cool. You can sonify, you don't need to do your own sonification, you can upload any kind of data and it will sonify it for you. So I think that's it. I think I was a bit short, but
Thank you, nice talk. Questions?
I think I killed everybody, sorry.
I have a question about so the first half of master program. Yeah, so I saw some people came from bioinformatics. So did they also do something project in astronomy, and why are they? What was their motivation?
So in the project part, well, the motivation normally is that they know somebody that came to the school and they heard that they can go to the observatory and they want to do that. But in the projects, we do not only have projects in astronomy, we have projects in NLP applied at different things, and we do have every year at least 1 or 2 projects on image processing related to biodata. So tomography, there is always something about detecting cancerous cells and things like that. So some of the students, again, mostly because they can go to the observatory, but some of the students, they know that we do this kind of projects and that we don't use proprietary software, but that we teach them how to do image analysis on their own and all of that, and that becomes quite attractive because many of them, they don't have a background in computing. So yeah, that attracts them.
More questions?
Hi, Emilia.
You can answer yourself.
No. No, I was wondering about one particular part that you showed. And so we've been discussing this with some colleagues, but how can you teach in like 10 days presentation skills to the students?
I mean, you definitely cannot, but one thing that you can, I mean, you cannot, that's it. We do have, yeah, I think you were already not so in anymore when we started to do this. Where we do give them feedback on the presentations also. So at least they have several practice with feedback. But I think more than teaching them how to do presentations, which is not easy at all, what we want is to teach them that you can be comfortable talking to others and that you can, you know, we have all the different accents. For instance, I really try, you know, to talk a lot. So another of the other co-chair is Matthew Graham. So if you know him, like, you know, his perfect accent, his perfect English. So I just go there with my stupid accent and my really bad English and say like, look, I can talk as much as he can. I can show you cool stuff. I can teach you stuff. So don't be so afraid. So yeah, we cannot teach them to give awesome presentations, but we can teach them to be less scared, to see from others what works, what doesn't work. And hopefully that makes them then improve.
Time for one more question, if there is one. Over there.
Thank you for the presentation. I'm just curious about all of the knowledge that you're gaining about how to teach this demographic and this group. Are you collecting that knowledge somewhere? Are you that all because I'm worried always with things like this that the knowledge goes out of the field when the teachers retire.
Yeah, so the technical knowledge, and that is a very bad answer. The technical knowledge, yes, the technical knowledge, in fact, that I didn't say. Every year we put all the material public. So the technical knowledge is there. The soft skills knowledge and what worked, what didn't work, what we learned from this. Unfortunately, I mean, it goes to grant applications, but it doesn't go anywhere. And you're right, that is a pity, and we should do better. Probably we should like have proceedings or something, not proceedings, but documentation of what we learned from this school that doesn't go only to grant applications, but to the public. You're right, we don't have it.
Okay, thank you. That's the end of the session. I'd like to thank all the speakers again. I guess the opening ceremonies are starting.